Good morning. Yeah, it's working now, isn't it? Good morning. I hope you had a nice evening in Oslo yesterday. So Farrokh, Nadim, and we were asked to introduce day 2 by telling you about some of our experience in practice with tailings storage facilities. Yesterday, we heard many great research achievements on advanced laboratory testing, in situ characterization, numerical modeling, and earthquake, dam break, and runout analysis. We will hear more today about the advances in remote sensing, geophysics, and environmental issues. Research is good, and we too, Farrokh and I, we strongly advocate research. But there's also the world of consulting and solving the questions asked by our clients. My first encounter with containment facilities in the early 70s was with tar sands, and then phosphogypsum stacks in Florida, and then many dredge materials in the US. The jump to mine tailings storage facilities was natural. Early on, the focus was on assessment of stability and observations of deformations. And in the 2000s, we were asked to do risk assessment. And all along, NGI was engaged in different types of expert boards. As an introduction to day 2, Farrokh and we thought we could tell you about work on ITRBs, Independent Tailings Review Board, and about risk assessment for TSF. So first, about RTRBs. An RTRB is a group of 3 or 4 persons, specialists usually, acting as a team to help an operator or an owner to make decisions. Expert boards have been used for TSF for over 30 years or even more, under different names. But the ICMM, in its voluntary global standard, GISTM, which we mentioned yesterday, has made the establishment of an ITRB as standard of best practice for the TSF with high and extremely high consequences. So suddenly, with the advent of the GISTM, there's a large demand for experts to serve on these boards. The role of the RTRB is to help the operator minimize the risk of a catastrophic failure, and that's because of what has happened in the past. And it's also the role to challenge the TSF project team to meet what we call the 3 R's: resilience, robustness, and reliability. Mark the word reliability. The RTRBs are to ask questions, to challenge the assumptions in the design, construction, operation, and closure, and offer experience with internationally good practice. The RTRBs are told to look at the big picture and to have a high-level and long-term and risk-focused approach to the facility. It's also stated in our terms of references that we should think out of the box. I've worked on expert groups or RTRBs in several countries and many companies, so my comments today are general and not for one company, one country, or one site. Most often, the RTRBs where I have been part of, they're for TSF that have been operating for a long time, and many of them are in the closure or post-closure stage. And again, this is due to the fact of the unfortunate events that have happened. So the experiences I've had, well, in one case, the RTRB I was working on was the enemy. We were perceived as being there to find fault and certainly not to help provide a safe solution. It was due to both poor communication within the company and the personality of the responsible for the project, who felt that the RTRB was an impediment to his work. It was a he, it was not a she. It happens. maybe the RTIB was useful that time because that person was replaced. But usually there's better preparation within the company. So we often divide the TSF into 6 components: water, leachate, or both; the retaining structure itself, which is sometimes looks like a dam; residues, the tailings; the 4th is the hydrogeology; 5th is the foundation; and 6th, the exit or the pond, where the water goes and whether it will cause contamination. So it's a very complex problem for people who are specialists in, let's say, 4 different areas. Usually, for all sites, there is a significant lack of information. The water balance is missing. There are uncertainties in the hydrogeological features. The riverbeds have changed. There are currents under the foundation or within the foundation. Some documents are not updated or do not exist anymore. It's due to change of personnel or other reasons. But our findings in many of the TRPs that maybe the companies, the operators, should have an electronic system in order to keep track of their documents and keep track of what are the latest editions. So that's a lot of work to try to find out through this enormous amount of information. Uncertainty in the foundations, which were mentioned yesterday, are very important. And there are significant uncertainties. Most of the areas that have been used, the foundation was not even investigated. Since the 80s, NGI has been on the board of expert, it's not called an ITRB, for the Zelasny-Most TSF. It's the largest TSF in Western Europe. It's about 4 kilometers in diameter, so it's an enormous area. Most of the problems are due to shear zones in the foundation and not the containment structure itself. Yesterday, we heard about advanced laboratory testing and advanced interpretation of in situ and laboratory tests. In many sites that exist today, there's only the simplest of laboratory tests that are available. New investigations are usually undertaken, that's correct, but these are subject to the local practice, and not all consultants are competent. Not all countries have the same level of expertise either. I mean, I've worked in countries as far as South Africa, and so the local practice is recognized as being best practice, but in our eyes, maybe in Norway, it's not the same. And it is difficult to get an acceptance that the direct shear box test does not give the same result as the direct simple shear test, and that the triaxial test should be anisotropically consolidated. And as we discussed yesterday, not everyone knows how to interpret the critical state line in practice, or how to identify a material that's susceptible to liquefaction. Fortunately, today there seems to be very wide acceptance that the CPTU, the pisocone, is one of the better tests in situ, and the greater acceptance that we can run many of them over a wide area. Yesterday, it was said that we are drowning in data. No, we are not. Not in many of our consulting projects. For the large containment areas, we have very little data to characterize sufficiently the behavior of the tailings or the foundation. The best practice test methods are not all we use, so it's very difficult for an expert board to interpret the data. The same also applies to determination of the geochemical properties, which we will hear about later today. So one of our challenges to all of us here, our community, which is majority is a research community, is to convince the TSF operators to adopt best geotechnical practice for the residues and for the foundation. So no, we are not drowning in data, and certainly not in high quality data. And surprisingly, in a way, the dam break analysis and run-out analysis and the earthquake analysis sometimes are excellent, and probably that's because they are more recent. But they can be also variable depending on the consultant. Now, just a few words. What about the RTRB itself? When you're in an RTRB, you do not choose who are the other members of the RTRB. Some are great, very knowledgeable, you learn a lot. Some can be irritating, some tend to dominate without doing any work. But we adapt, it usually goes well. And one important aspect, the RTRB needs to speak with one voice. Sometimes some of the RTRB members simply do not understand this, and they keep sending messages to the operator without informing the other members. Very irritating. So not all are effective, and honestly, one of the members always ends up working more than the other three. In closing on the RTRB, and I suspect that some of you already are on RTRBs, as some will certainly be asked to serve on an RTRB someday. The RTRBs are there to help the TSF owner from a perspective of risk, such that the owner's decisions are risk-informed decisions, because there are many uncertainties. Now, over to you, Farrokh.
Thank you, Suzanne. My name is Farrokh Nadim. I've been at NGI for almost 41 years. I think next Tuesday is going to be exactly 41 years. But one of the problems of working at NGI is that no matter how long you are at NGI, you're always a junior. There's always somebody here who has a lot more experience than you. So I still get homeworks from time to time from Suzanne, from Kåre Høeg, from Kjell Karlsrud, people who have a lot more experience than I do. Actually, yesterday I was just doing search, which was my first tailings dam project or tailings project. And as a big surprise to myself, my first project was already in December 1991. It was a project called Zelozimos Geotechnical Safety and Environmental Hazard. And the summary of that report, we start off by saying static and dynamic stability analysis indicate that the dam has adequate geotechnical safety. However, the properties of the subsoil and the tailings should be determined by improved laboratory methods for future stability analysis. And I guess the discussions that we had yesterday kind of drive home this point, that the methods that we use still today for estimating or evaluating the properties of the tailings especially, they still leave you with a lot of uncertainty. And that's why I guess one of the reasons that the GISTM standards, they recommend doing risk assessment for TSF, but they do not specify how this should be done. Now, following up on Suzanne's words on the importance of risk assessment, both Suzanne and I were involved in doing risk assessment for offshore structures and for water retaining dams since the late 80s, early 90s. And then through the Zelozimos project, I got the job of doing a review of a risk assessment that had been done by another consultant, by D'Apollonia, which was a really excellent report. But what struck me at that time is that how much conservatism was made in this report, and then how much focus was given to earthquake loading, whereas there are many other problems there which are much more important than earthquakes. Of course, if you're working in a country with very high seismicity like Peru or Chile, that's the main problem you should be concerned about. But that's not the only problem. No, since then, I've been involved in risk assessment for quite a number of tailings dams. Maybe the most involved one was the Roșio Montana gold mine project in Romania. And that's a tailings dam that's never been built. It's become a very political issue. Our involvement started in, I think it was 2006 or some around that time. And we were involved in 2 rounds of this risk assessment. And the way we do it, okay, it's not the only way that it can be done. But the preferred way of doing it from NGI side is to organize these event-free workshops where all the people, different expertise, are gathered in the same room for a week. They visit the site. They go through all the documents, and then they start discussing all the scenarios that might lead to a dam failure or a dam breach. And just through these discussions, you find out issues which are really easy to address, but nobody had thought about them before. And in Rosia, Montana, maybe it's not a good example because that dam has not been built, but I did end up testifying in the Romanian parliament, which is the largest office building in the world. Actually, it was built, the castle that was built by Ceausescu. And so I'm not going to dwell too much on that thing. Then I got involved in a project in Peru, and there, again, the engineer of record had the foresight to recommend doing a risk assessment. And because he didn't think that, or they didn't think that the procedures that were being followed are safe enough. And they basically threatened that if the owner didn't do a risk assessment, they would resign as engineer of record. And then NGI was contacted, and I was fortunate enough to get involved in that project. And again, the main focus was on earthquakes, but as it turned out, they had a lot more serious problems to think about, just when they discussed it among themselves. And some of these problems were very easy to address. And hopefully, through that process, it made it safer. Then in November 2015, the big disaster in Brazil happened. And we got involved, me and Hans-Peter Josta, I don't know if he's here today, he made a presentation yesterday. We were there actually 1 month after this catastrophe as consultants to the state attorney of Minas Gerais. And our conclusions are why this thing happened are somewhat different from what that famous report, the committee that everybody refers to. But unfortunately, we're not allowed to discuss that because that case is still in court. But that was my first experience of seeing, how serious these problems can really become. And one of the strange experiences was that we were walking on the part of the dam that hadn't failed yet. I mean, the rest of it was gone, but we were just, doing the site visit. And one of the people was working there. He said, just stand there. And then he started jumping up and down about 20 meters from us. And after he did that like 3 or 4 times, you felt that you were standing in jelly. It was really an uncomfortable feeling. And so these people were quite aware. I mean, this was like a game they were playing on these tailings. And that's the sort of material that you could experience static liquefaction. In my opinion, there's so much uncertainty in this phenomenon of static liquefaction that it's impossible to say this is going to happen or not happen. You have to deal with uncertainties, and I think those presentations yesterday drove home this point quite well. And when you're dealing with uncertainties, you have to address them head on. So you cannot say, okay, I'm going to be conservative in every assumption, then you do your calculations, you end up with a safety factor of 0.2. So what? I mean, the owner of the dam is not impressed. So our dam is standing there. What do you mean the safety factor is 0.2? So you have to say, I mean, think about, how things can go wrong. What can you do to improve the situation? What's the risk? What are the consequences? And these things can only be addressed in a reliability-based approach where you address the uncertainties. In our opinion, running these risk assessment workshops is very helpful, even though your probabilities are not exact, but they represent the best judgment. But there are many ways of doing it. Any way you do it, you shed more light on the problem. You maybe find out ways that you can reduce the risk. And at the end, everybody is better off by doing these risk assessments than not doing it. Thank you.
So very warm welcome to everybody. I hope you had a great start today with Suzanne and Farrokh talking about their experiences. And moving ahead with the first technical session of today, which is related to remote monitoring and geophysics. So we have the first female in the house to deliver this talk today. So it's Regula Frauenfelder from NGI. So she's been a technical expert with us, and she specializes in remote sensing, geomatics, and natural hazard research. She also holds an adjunct associate professorship position at the Department of Geosciences at the University of Oslo. So the floor is hers, and with the message that the mining industry now has to listen to more women in the field. Yes.
Okay, yeah, thanks very much. Good morning, and thanks for the introduction, Sparsha, and none the least for the invitation. And the task you gave me, because Sparsha asked us if he could give a short talk about remote sensing of tailing storage facilities. And I thought, I just kind of present the results we have from the SB12, from this project that Luca presented earlier yesterday. And then she said, no, but you know, you're the first one in the session, so please give a little overview. So I tried to make my talk a little bit broader than originally planned. I would also like to acknowledge the co-authors that are kind of participated in the work that I'm going to present. That's my colleague Malte Vöge, Luca, which you already know very well, and the master student that we had from NTNU, Ida Svensson. I will first give you a short overview on available techniques, and it's by no means meant to be kind of really touching everything, but just giving you a flavor of the variety of methods that we have today. Then I will dive into a case study on how we use remote sensing for displacement monitoring, how we use it for hindcast measurements of failures, and then wrap up with short conclusions. The first point, and as I said, it's a non-exhaustive overview on available techniques. I'm sure there are others out there, but I just kind of tried to mention the most common ones. Starting with the, let's say, simple methods. You have an automatic total station, you have reflectors at your tailing dam, and you just measure this one point either continuously or in intervals. You can do that more broadly with LiDAR, light detection and ranging sensors, either terrestrial, also from a tripod, or putting it on a drone, or putting it on a plane. And then you get point clouds that measure the geometry of a dam. You can use multi- and hyperspectral image analysis, and I will give an example of such an analysis afterwards. You can use interferometry, satellite-based or ground-based, and that's where my case studies will be from this technique that I will show you afterwards. You can, of course, also have a lot of in situ instruments and use them real time, and we have big possibilities now with these also these IoT sensors and with real-time data transfer. And then you have what I would call as a remote sensor. I call it the quasi-remote sensing techniques, such as ground-penetrating radar, seismic sensors, DAS, distributed acoustic sensor, and then, of course, it's like a transition over to the geophysical methods. Now I just show you a couple of examples that are not from us, but that I found in the literature that shall highlight some of these techniques that are mentioned here. The first one is a study that was done by Martin Velázquez and co-authors on erosion mapping of tailing storage facilities and their slope characterization. And this was done by aerial LiDAR. So they mounted this LiDAR tool on a plane and flew over in 2 different years, 2009 and then 2014, and mapped the topography of this tailing dam facility. You can see there are 2 points, one to the north, one to the south. You see the slopes here that have here is shown the slope angle. Green is flat, and the redder or more orange it gets, the steeper it is. And then they did an analysis of the changes. And the changes there are several, but they're not all very easily visible. But you see, for example, up here, you start to see that there have been slides from the tailing slope that kind of then lead to this flow-like or landslide-like features. And that's, in their paper, they analyzed that in more care. But that's just one example of aerial LiDAR. The next one is actually, it's this one by Zhang et al., but I also show you this, this plot from the wavelength spectrum, because you can then see that different type of agents have a different reflectivity through the wavelength spectrum. And here, for example, you see like tailings, iron ore, they're in the middle here, whereas the soil, for example, is up here, water down here. And you can then use that to differentiate different type of minerals on a tailing pond. And that was then done, as I said, by Zhang et al., that they here were able to differentiate where they had the biggest fractions of certain type of minerals on this tailing pond. And that was done by using hyperspectral image analysis, also from a hyperspectral sensor that then also was used you can do it from a satellite, depending on the resolution, or also from an airplane. Another technique, deformation mapping, and we're going to get closer to the core of the talk. This is an example not from a tailings, but from an open pit mine, where you see we have the ground-based interferometry radar here, pointing towards this open pit free face, and is then also, you can then also measure if there is some displacement between the individual measurements. Here, everything which is green is stable. Blue starts to have a certain kind of motion, but then if you would have a red, then you have kind of motion, and that's here mostly that maybe stones that have either fallen out, or actually here it's that they had excavated this part between the measurement 1 and the measurement 2. And of course, as I said, that's an open pit mine, but you can of course also use that if you would use the same technology looking at the front of a tailing dam. I was mentioning real-time sensors, IoT, Internet of Things sensors. You can have them today in all kind of varieties and types. You can measure also a variety of parameters, from pore water measurements to deformation measurements, settlement profiles, and you can then have tools and interfaces where this is directly transferred into your monitoring system. This is from a non-tailing project at all. It's from a railway project, but just shall show you kind of the principle. This is then the interface that my colleagues at NGI can have access to, and here, for example, are real-time inclinometer measurements that are also already color-coded, and all the green ones are not kind of, they're stable, they are not of concern, whereas the redder they get, the more deformation is measured, and then you can also, of course, implement threshold values where, for example, internally or externally, there would be issued an alarm to the people in charge of monitoring these things. And these are possibilities that you also have to a certain extent on tailing dams facilities today, if you use such type of measurements and data transfer. Then I also just digging into the literature. Of course, AEI, artificial intelligence, has also started to have his imprint on monitoring of dams and tailing dams. Here they did automatic or AI-assisted monitoring of erosion on a slope. I won't dive into the details how they did it, but just show that that's things you can do today with if you have this type of measurements. Here they just use visualization. You have a lot of possibilities to visualize all these measurements in maybe ways that we didn't have 15, 20 years ago. Here, another AI-assisted example, but you could also do that without AI to measure the size of the free water phase on a tailing pond as compared to the more drained tailings on the surface. And then, of course, you have the possibility, once you have, for example, all these terrain models that I showed from the LiDAR in that first example, you can trace profiles and can see if you have two profiles from before and after, for example, how things have changed, not only kind of looking at the map, but also kind of doing transects. So this was it a little bit kind of from the review of the different type of measurements and possibilities we have. And now I would like to dive more into the core of the case studies that I would like to present. And before I do that, I would just shortly give an introduction in the principle of interferometry. And I hope not everyone is kind of totally known with this technique and thinks, oh no, boring. We've had that like a long time ago. But the thing is, the technology uses actually the same principle as a bat. You send out a signal, and a signal is coming back. Here it's a sonar signal, and looking at, for example, an insect, we are looking at the Earth, and we are doing that from a satellite, and we're sending out a radar signal. But the principle is exactly the same. You send something out, and you get it back, and you measure the difference. A SAR signal, synthetic aperture radar, and it's just called synthetic because it would be impossible to build such big antennas that it's not synthetic anymore, because then the satellites would fall down. So we try to not do that. That's why it's called synthetic. But this signal that's sent out has an amplitude and a phase. The amplitude image shows a recognizable, for example, topographic pattern. This image is not SAR, that's optical. But the next one is SAR. And you see, you can recognize. It's kind of almost showing almost the same. It's just in black and white, and you have some distortions down here, maybe of the mountains. But I mean, you still kind of, you could interpret that image without having any SAR knowledge. That would be too easy, so we use the phase of this wave. And the phase does look a little bit different to the human eye. It looks like this. So it doesn't really tell you anything before you start to analyze it. And that's why you need at least two of these images. If you have a large deformation, like from an earthquake, you can use two images, because then you measure the difference, the interference of these two images, to calculate, for example, the terrain model, or in our case, we are looking for the surface deformation. And if you combine two, then it starts to look like this. Because then you start to see these fringes, we call them, kind of between the difference between these two scenes or images that you have used. Here we're looking at the glacier, so it's again a totally different application, but I need to take something that had a fast enough deformation so that we actually see something. However, in tailing dam monitoring, we would be interested in the slow measurements, slow movements. And then you need a long stack, many, many images. And then if you start to add them, you would start to be able to see the deformation. And if you have a short stack, you see the deformation that has happened in this short time interval, and if you start to have a longer time series, you can start to see longer deformations. One thing is maybe also important to mention, which is kind of not that practical, because we sometimes have a lot of grass and so on tailing dams. Vegetation is not our friend with these measurements. So the more, I'd say, artificial objects we have, the better. So railings on dams, for example, or if you have a hydropower line, all that stuff is kind of favorable. But you can get measurements on vegetation. It's just much easier if you also have some other artificial signals. And I would like to show you the first case study. We've heard about Selassie Most before. Largest tailing dams in Europe, constructed a while ago. 75 meters high upstream dam. That's what it looks like if you go into Google Earth. And that's what it looks like if you do an INSAR analysis. You see, where it's gray, it's stable, and the redder it gets, the more deformation we have. And what you see here, this red crown, that's the natural settlement of the tailings towards the center of the tailings. So we're not preoccupied about those. But when we did the analysis, we also saw this little bulge here, which is kind of outside the crest. It's on the outer slope of the tailings, so we wanted to look a little bit more into detail of this one. And then you see that you actually have this more or less continuous deformation. Here we have 2017, 2019. There's a little kind of decrease around 2018, but in general, you have this kind of decrease. This was done analyzing data from only one orbit, because I mean the satellite is orbiting around the world, and then you can have, it takes images kind of when it comes down and then also when it comes up again. If you have images from both these orbits, kind of when it's going up and when it's coming down, you can decompose the signal you get, because what we normally do is we just kind of analyze this vertical velocity, but then you don't know if there's also a horizontal component. And this is what it looks like when you do this decomposition. You can get the horizontal east-west deformation, and then you see everything that's purple is going towards west, and everything that's green is going towards east. And you see again, of course, in the middle, the natural deformation towards the center, so it's logical. Everything from the east goes to the west, and everything from the west goes to the east. But you also see also the dam, the outside of the dam on the western side is going slightly to the west, and the other one is slightly going to the east. So we have a kind of an interesting deformation pattern here. I leave that to the specialists in here to interpret that. We didn't go further with that. And I won't either. It's just to kind of show you what kind of possibilities we have. The second case study is from these hindcast measurements, and here the Fechal tailing dam. It's also an upstream dam, higher actually than the Zelazny Most, but much smaller in size, which experienced, unfortunately, a complete failure on January 2019 and caused many, many fatalities. And I will start this video, and just the important thing is down here, where one sees that actually the breach started in the lower half of the tailing. That's what it looked before, that's what it looked afterwards. And this is the INSAR measurements that we did. And here, just to point out what I said about vegetation, the forest just doesn't give us any measurements. Not that we would have been that interested in that exactly that forest exactly there either, but it just shows you that there are some limitations for the methods. You also see that down here, where we would be most interested, there are not that many measurements. Again, you see up here the natural settlement of the tailing, but then we come into slope and we still see that something is happening. If you do it like in these portions, you see the green one, the green area, that's kind of seemed to have experienced more or less continuous settlement, even slowing towards the failure, according to these measurements. Down here, we see a similar pattern. But then if we look where it actually failed, we also see that it's deforming, but we think we actually start to see an acceleration here towards the end of 2018. And we don't have a data point after the 22nd, because the satellite just didn't come by between 22nd and 25th, so we have to use the data we have available. You can then look at the inverse velocity analysis, and I believe we will probably hear more about that from Emanuele afterwards. And then look at these last points in the time series and get to an estimate of the failure date. The first time we did it, we came 2-3 days earlier than the failure. And then we had this master student, and she did a lot of filtering and tweaking, and actually ended up sometimes even at the failure date. Our point is, yeah, it's this regression, this analysis gives a good fit, and you can get to quite close with the prediction of the failure date. As I said, our range was 3 days prior to the correct date, but there is a large source of uncertainty also here, because we do quite strong filtering of these points, and then after the subsequent regression, we have a certain signal-to-noise ratio that we also have to take into account, and nonetheless, we very often have a low number of data points close to the point of failure. But it can give you an indication, but it's a hindsight analysis that we show here. So as to which degree you could actually use it to say something about the failure that has not happened yet is, which stands to see. So to conclude, what I hope I could shortly show you that we have an abundance of remote sensing methods and real-time remotely accessible sensor data today. So there are a lot of tools around, which give us, in my view, quite an unprecedented possibility to monitor tailing storage facilities. But I think it also demands for a higher level of understanding of the pros and cons of these methods. So you should know which method you apply for which problem and how to interpret the data that you get. We believe that the INSAR is quite a suitable tool for long-term displacement monitoring of such facilities. But I also indicated some challenges that you have to keep in mind. If present, maybe with caution, but we think that kind of precursors that lead to a breach should be able to be detected, and that this inverse velocity can be used. But as I said, there are large uncertainties that have to be considered. So yeah, you can use it, but use it with care. And with this, I think I'm at the end of my talk. And if there are questions. Yeah.
Thank you so much, Regula, for setting this stage. I think we'll take the questions at the end after we have all the speakers. Yes. So maybe I'll have you back on stage after the 2 speakers. So now I would like to welcome Emanuele Intrieri from the University of Florence. And he focuses on remote sensing for tailings dam deformation analysis within landside risk and cultural heritage preservation. So the stage is yours. Yeah.
Okay. So good morning. Thank you for introduction. And in my presentation, okay. No. Okay, just a matter of pressing. Okay. So as Regula mentioned, I will talk about forecasting. If it is possible to make some sort of forecast about the failure of tailing dams. Part of the data that I will show have been elaborated by Regula herself and Malte Wöge, that I also wish to thank. Forecasting, as you know, is a component that it is nested within the larger framework of early warning systems. So we have already talked yesterday about the importance of the design and the geological knowledge of a tailings dam. About the monitoring, as Regula told us, and there are also some aspects concerning more social issues like risk perception and so on. But now I will focus on this other component that is the forecasting. When we talk about forecasting using displacement data, we mostly make reference to the creep theory. I assume that you already know about this, but just to be on the same page, creep is a model where in a slope, for example, or a tailing dam, or a man-made structure experiences some deformation before failure. And these deformations are traditionally separated into 3 stages. So there is a first stage called primary creep that is characterized by deceleration, then a secondary stage characterized by a constant velocity, and finally a tertiary creep that is characterized by a power law acceleration that ultimately can lead to failure at this point. But this is, of course, not always the case. You can have decelerations at any time. You can have a start of what looks like a tertiary creep, but then you have like a false alarm, and maybe the slope is again stabilized. So what is difficult here is to detect when you are at the tertiary creep, and from this point on, you start making your models. The first one to deduce the importance of this model was Saito. He developed the method, the graphical method, and also a numerical solution, which is not difficult, but it is also not so much straightforward. So this method is not very much used nowadays, and it is more used than this method is this solution that has been found up by Fukuzono, who realized that if the velocity is going to increase theoretically towards infinite before failure, then the inverse velocity is going towards 0. So if we trace the inverse of the velocity and we extrapolate the point when this value goes to 0, we can find the moment when theoretically the landslide or the tailings dam or any even man-made structure are going to fail. So this is the classical approach, and in the next few case studies I will also show tentative of making a reiteration of these methods. Reiteration works like this. We, instead of making just one prediction, we want to try to improve the confidence of these predictions, and by making by stacking prediction made day by day or measurement by measurement and so on. And so, for example, in this graph here, you can represent the predicted time of failure on this axis, and on the horizontal axis, you can plot the time when that prediction is made. So, for example, you can have a landslide like this, that is a landslide in Italy, which occurred in 2002 on the 28th December. This red line represents the actual time of failure, and day by day you try to make a forecast, and you see that this point, the triangles and the crosses, they oscillate around the actual time of failure. The crosses represent the prediction made with Saito method, the triangles with Fukuzono method. The diamonds are predictions made with another method developed by Mufundirwa et al., not very known. But as you see, it never converges and it never oscillates around the actual time of failure. So it is not a pretty good solution, at least in this case. Just one more example before going more into the tailings dam. This is an example of a prediction made with hindsight of a copper open pit mine. So we have seen so far how we are able to make prediction of failures, which is already difficult. Even more difficult is to try to make predictions using satellite data, because satellite data they have not so high acquisition frequency. So you have one acquisition every few days. So it's difficult to get the tertiary creep. But it is possible. There are some cases that show us that in some cases it is enough, this acquisition. So this failure here has been monitored by both a ground-based SAR which is these colored pixels here, and the triangles represent measurement points detected by Sentinel-1, so by satellite. And in both cases, Sentinel-1 and GBINSAR, we found pretty nice linear trends when we calculated the inverse velocity that would have enabled to make a pretty reliable prediction of this failure. So as Suzanne said, the reliability is the important thing here. Then we can add a further step for the difficulty, which is using forecasting methods, applying Sentinel-1 data, and applying them to tailings dams. Tailings dams have two more issues. One is that the collapse is in general quite abrupt, and the other one, as Regula just underlined before, is that we have more or less constant deformation all the time. So it is not always easy to detect a clear onset of acceleration. You may think that you are entering the tertiary creep, but maybe it is not the case. So the first one is the case of Cadia in Australia that failed in March 2018. In this case, we have a pretty neat acceleration, and you see that this acceleration is also quite long, so it lasted for several weeks, which is something that allows for a relatively reliable prediction of this failure. If we see something like this, it seems so that maybe it was easy to make a prediction, but if you compare this prediction with the case I showed you before from the copper open pit mine, or for another landslide, Shinmo landslide, which is another famous landslide that occurred in China, you can see that the displacement time series in all these three cases, and also in the Cadia tailings dam, are apparently similar. The inverse velocities are also apparently similar. You see the R² value are all the same. But then if you try to measure the error, you see that the reliability of this last prediction was a bit lower. In fact, these three curves have been obtained by making an average of many different measurement points. For example, in this case, in the copper open pit mine, we put together 78 points, displacement points. We make an average, and we extrapolate these two graphs. But what does it happen if you make the prediction for each one of these 78 points? You obtain 78 different predictions, and for this copper open pit mine, these 78 predictions are all focused around the actual time of failure. So they give you very similar results. With the Shinmo landslide, we had 125 points. We have a little bit more dispersion, but still the average time of failure was pretty clear. With the Cadia tailings dam, you see that, first of all, we have two modes, and then we only have 20% of the points among 123 that gives us the real time of failure. So this experience here shows us that forecasting of tailing dams is possible, but the reliability is not as much as with other cases. We can also try to make a reiteration, as I showed you before, the predicted time of failure, the time of prediction, and this is the actual time of failure. The greenish lines represent predictions made with older data and are basically never converging or are very noisy. The purplish lines, which are here, blue and purplish line, they use only newer data, so they are shorter, and they start to show a sort of oscillation, but it is not around the actual time of failure. So as I said before, also in this case, this elaboration tells us that the confidence of prediction would have been not so high. This is the same with Saito, but similar results. Then there is Córrego do Feijão in Brazil that Farrokh mentioned before. and Regula as well. These, in fact, are data, the data that show Regula just a few moments ago. And this is a paper that I found in the literature from 2020. In this paper, the authors tried to make an elaboration using SBAS and PSI algorithm, and they both give, of course, they give slightly different results, but they are in line with what Regula showed before, which is that the prediction is somewhat possible. It is, of course, a prediction because it was made with hindsight, and the error was around 8 to 10 days. Also, the acceleration is quite small. It's not much different than other smaller events. So again, this experience tells us that, again, maybe in this case, monitoring made with another instrumentation that gives us a higher acquisition frequency probably, maybe, would have allowed us to characterize this acceleration a little bit better and maybe to extrapolate an inverse velocity that probably could have been more useful. So this is a borderline case. Was prediction possible? Maybe. I'm not very certain about that because again, the reliability was even lower than with the Cadia lenslet. And this is the reiteration of the method that is even more noisy than earlier. Another case study is Jägersfontein in South Africa. It occurred almost exactly 1 year ago. And the tailings dam was very peculiar because the deformation has this strange behavior. At least I'm sure that many of you who are more expert than me in tailings dam can give an explanation about this behavior. But for me, it's who I come from lenslets, and this is quite peculiar because we have this acceleration, then finally a deceleration, and at least for one measurement, but we cannot give too much importance to a single measurement. So, but the trend is quite clear. And what's interesting is that if we dismiss these final acquisitions, and if we try to make an inverse velocity only using data until this point, we obtain a pretty good prediction. But I am almost certain that this deceleration would have sent many experts off track, because this really looks like the tailings dam has reached a sort of new equilibrium. And so again, this is an even a third case that tells us that about the difficulties of making prediction of tailings dams. Finally, as a counterproof, I want to show you Zelasnimos. Zelasnimos never experienced a failure. So this is, I add this case study just to show what happens if we apply these methods to a tailings dam that has nothing to show. Theoretically, we should see nothing interesting, no convergence, and fortunately, this is the case. So this is about 1 year of deformation. You see that the trend is almost linear, and in fact, the inverse velocity never gives you a prediction because it never touches the x-axis. So this is like a counterproof to show that the cases that I showed you before were not completely mistakable with a case where everything is okay, everything is normal. But there are some still some difficulties that put us in a, let's say, in a pre-warning zone. So we know that something may take place, but we are not sure if it is something that really necessitates to halt every activity or not. So if, as a final summary, if we see together the 4 different case studies that I show you, they are pretty different. So we have the Cadia tailings dam with a clear and long acceleration, corregado Feijão with a small acceleration that tells us that maybe some other instrumentations probably could have provided us with more useful results. Then there is the Jaeger's Fontaine that tells again that in some cases probably even with good data, something within the mechanism of tailings dam it is really intrinsically difficult to predict unless maybe something takes place between these two final measurements. Maybe if we have some, like GBINSAR, maybe we can see some precursor lasting just for a few hours. And finally, a case like Zelasnimos that tells us that there are also cases where we know that we cannot make probably false alarms. So to conclude, what is the state of the art of predictions of tailings dam failures? We have three difficulties. The first one is that making prediction is per se difficult. The second one is that we add the difficulty of using satellite data. And the third one is that tailings dam are particularly complex for the reason that you know. However, we have shown that it is theoretically possible. So it is worth continuing on making trials and errors and research on this topic. In particular, Sentinel-1 is probably groundbreaking with these applications because for several reasons. It has a large swath, so we can monitor entire tailings dams. We have a decent revisit time. It used to be 6 days, now it is 12 days. And also data are free, which is not bad. GBINSAR monitoring could be even more important, but at least I can cite the example of Feijão in the technical report that Farrokh mentioned before. They say that they have GBINSAR data, but they were not useful because they didn't see any precursors. But I have not seen this data. I think that they are not published, at least I didn't find them. So it's difficult to comment on this. But in any case, this tells us two things. One thing is that GBINSAR are very powerful instruments, but they only cover a portion of especially very large tailings dams. So you maybe need many tailings dams in something, like just think about Zelasnimos, for example. Another thing is that to make research, these data, even if they are available, they are not always published or publishable. So for the scientific community, the Sentinel data remain, Sentinel or other satellite, of course, remain probably the main resource because you can cover the whole area and also because they are available. So we can try to make models using this data. And this is it. Thank you.
Thank you so much, Emanuele, for the interesting case studies. No matter how much we want to stay away from the tailings dams doing remote sensing, we actually have to go on them. So now we move on to geophysics part of it. So we have Greta Tresoldi from LSI Lastern. So she's an environmental engineer and a geophysics expert and a product manager at LSI Lastern. And I think she actually has a sensor in her name, Greta. So she'll be talking about this. So looking forward to an interesting talk. The floor is yours.
Thank you very much for the presentation, and thanks NGI for the wonderful workshop. Okay, thank you. Today I will have this presentation. It's a little bit different from the others that we saw in these days because I think that LSI Lastern is the only manufacturer technology provider here at the workshop. And today I will have this presentation about a new solution for tailings dams monitoring. It is a geoelectrical monitoring system for permanent monitoring and automatic monitoring. So just a brief introduction about ERT measurements that are electrical resistivity tomography measurements. They are geophysical indirect measurements, so you can acquire a lot of data without digging and understanding the processes inside the dam body simply with analyzing the propagation of the electrical field inside the subsoil. So you can obtain a bidimensional section of the monitoring area. And why the electrical behavior of subsoil is so important. Since it is mainly related to soil composition, water content, presence of voids, and fluid resistivity. So it can provide useful information on the monitoring area. But how does these measurements work? First of all, you need the georesistivimeter, and you need cables and electrodes. The electrodes must be in contact with the soil, and thanks to these electrodes, you can inject the current in the soil and measure the voltage. So you need 4 electrodes, in this case each time, to acquire one measurement, and using different quadrupoles, you can acquire all the section and take a picture of the subsoil. Thanks to the second law of Ohm, you can relate the tension, the measured voltage, to the current and to a geometrical factor. So you can obtain these raw data, but then you need to process the data thanks to an inversion algorithm. These measurements have some pros, but also some cons. First of all, one of the main pros is that you can obtain a bidimensional data and not a punctual data. You can investigate large areas with only one system. We are speaking about hundreds of meters of section. And also, you don't have to dig to acquire the parameters of the soil. I think that the key factor is that these measurements are sensitive to water, so you can follow all these processes that are related to water presence in the soil. The cons of single ERT measurements are that they are acquired through long field work, and also when you take only one picture of the subsoil, you can have some ambiguities. So you cannot discriminate between, for example, saturation or, for example, different soil with different properties. Another thing is that the processing is not so easy. You need an external software. You have to process the data with this inversion algorithm. And also, if you want to repeat the measurement, you have to go again on the field, reposition the exact profile in the same place is not so easy. So we can pass from the single measurements, ERT measurements, to automatic monitoring. So passing to this automatic monitoring, we can overcome the main cons. So for example, the long field work, if you have a system that is installed in site, you have to go on site only the first time and do the installation that is usually quite standard. Speaking about the ambiguity, obviously, if you have only one picture, you can not understand these absolute values. But when you are making a monitoring procedure, you have like a movie of the subsoil, so you can follow the processes. And these processes are mainly related to water evolution in the soil, cavity formation, or fractures. The processing of the data, if you have an automatic monitoring, is automatic. So you don't have to every time take another software and analyze the data separately. And also the repetition is not an issue, because if you have a system that is installed, the measurements are remotely done and they are automatic. So what can we do with this ERT automatic monitoring? For sure, we can follow the underground processes and also solving the problem before it's too late, because when you see it with your own eyes, it's too late. So this product that has LSI Lastern with Polytechnique di Milano University developed during a research project almost 8 years ago. It is an off-the-shelf, autonomous, cloud-based solution for the permanent geoelectrical monitoring of many different fields. In this case, we are speaking about TSF. The system is composed of hardware that is a georesistivimeter inside a box with the pole and the solar panel, so it is totally autonomous from an energetic standpoint of view. It has two long cables. We are speaking about also to 200 meters. It has 48 electrodes. You can cover the electrodes with soil in a shallow trench in order to permanently install the system. Then you have cloud software to visualize the data, make some data analysis, download the data, put some thresholds. So the main feature is the fact that this system is remotely programmable. You can obtain real-time data, and also the inversion of the data is totally autonomous. You can also integrate some sensors. So for example, rainfall in this application is really important since it changes the resistivity of the soil. So you can install also rain gauge, but also piezometers. Since these two measurements can be compared, piezometric level, for example, and resistivity, we can integrate all these data inside the same system. Okay, so speaking about the specific application, so TSF monitoring. Geoelectrical monitoring can give a hand in understanding the assessment of TSF stability over time, since resistivity measurements are function of the water content in the soil. They are really useful to understand if there are some concentrated seepage or under seepage, different saturation inside the monitoring area, and also the evolution in time of the saturation. We had also an experience in the watering project, and also obviously the identification of the groundwater level. So when we are approaching a ERT monitoring project, what we have to consider? The first part is common with mainly all the monitoring projects, since you have to identify the process. You have to identify the failure mode and also the cause of the failure. So you have to understand which are the parameters that I want to monitor, and this is the basic thing that you have to apply when you are speaking about a monitoring project. So if these processes are related to groundwater level, concentrated seepages, saturation, under seepage, but also cavities, ERT monitoring can be really useful. The second part is related to the implementation of the system. Obviously, when we are speaking about monitoring systems that are ground-based, you have to identify the most critical areas. You cannot put one system every meter. You have to identify which is the most critical part in your facility. Then you can also decide in which part of this area I want to install the system. For example, at the feet, at the crest, on an embankment. And this is related to the process that I want to follow. Obviously, if I'm searching for an under seepage, I have to install the system at the feet of the facilities. Or if I'm studying the dry part, probably I have to install on the crest. Then other important parameters are the length and the depth of investigation. Which part of my dam I want to monitor, and also which is the resolution, the data resolution that I'm looking for. These parameters are strictly related to the electrodic distance, because the number of electrodes in this system is fixed, but you can vary the distance between the electrodes. So larger is the distance, and bigger is the zone that you can monitor, but also lower the resolution. So you have to play with these three parameters. And then you have also to decide if your installation will be for long term, so mainly permanent, or for short term, that is months or weeks. In this case, you have to select the right type of electrodes. To be installed, for example, in the trench, you need plate electrodes or other kind of electrodes if you want to hammer the electrodes on the surface. And then the last part that is always critical, because it's really important to have data, but you need also to understand how to use them and to analyze them in order to make some decisions. So in this case, you can decide to follow the evolution of the resistivity, then mainly is related to the evolution of the saturation in the soil, or you can also decide to put some thresholds that are related to thresholds in saturation. You can also underline this homogeneous behavior, so for example, concentrated seepage in a part of the dam. Then we go directly to some case studies, since it is a really practical presentation. The system was commercialized in 2020, was not a good year, but we have these 4 case studies in the TSF world. The first case study is a copper mine in Chile. The second one is a gold mine in South Africa. The third and the fourth were installed this year in July and August. One bauxite mine in Australia and one platinum mine in South Africa. So we will go through these case studies. The first case is a short-term monitoring study. So the system was relocated in 2 different parts of the dam. So here you can see the 2 profiles. The first profile, then after a few weeks, the system was repositioned. In the site, there were 3 wells, piezometric wells, and the system was installed in order to monitor the phreatic level below 2 wastewater ponds. The monitoring aims were also the comparison with piezometric data and also the correlation with the variation of wastewater pond level. Here you can see the picture of one of the installation, the system, the solar panel, the cables. In this case are on the ground and not buried in the trench because the system was then relocated. Okay, just one data of the many different days that we were monitoring at the site. This is the typical ERT section. Here we can see the scale of resistivity going to really low values connected usually to saturated soils to high values. In this case, we can easily recognize 2 main layers. The shallow part is related to the dry part between the surface and 5-10 meters, depending on the exact point, and then the saturated part. This is the position of one of the piezometers, and this is the variation of the groundwater level during the test phase. The red dot is the day of that measurement, so we can see that the groundwater level that day was minus 8.5 meter, and we can see that the boundary between the 2 zones at that time was exactly minus 8.5 meters. So we can extend the data of one piezometer, we can obtain a section, and in this case, the correlation was really, really beautiful. Going fast to the second case studies, in this site there was a permanent installation. The monitoring aim was the control of the seepage and saturation in the TSF wall. And so the analysis was based on the average resistivity variation a long time. The installation site was the TSF crest. Here you can see the main step of the installation. So there is the step 0 for the connectivity of the system, the router configuration with the SIM card. Then the trench excavation. The trench, it's really shallow, 50 centimeter deep and 50 centimeter wide. In this case, the client had a big machinery, so the trench was really big, but it's not necessary. Then the installation of the plinth and the pole, the mounting of the box and the solar panel, then the unwinding of the cable and the electrodes, and these are the plate electrodes inside the trench. In this case, the profile was 140 meter long, and the depth was 22.5 meter deep. Then the step 4 is the coverage of the electrodes. They must be really in contact with soil to guarantee the electric connectivity. then the trench closure, and here we can see the platform and the monitoring area. The section is really homogeneous with really low values of resistivity. In this site, we don't have a piezometer, but we know that the groundwater level is around 18 meters. So here we can see the bottom part that is more conductive due to the saturation. The third case is the bauxite mine in Australia. Here you can see more or less the same picture of the installation. In this case, the monitoring aim was the post-closure assessment. So the pond was kept, and then we had to analyze an embankment downstream the pond in order to see that it's becoming drier and drier a long time. So the analysis is based on the evolution of average resistivity of this dry part of the embankment. This is the result of the first day of installation. You can see that we can identify two really different parts. The shallow part with not high, but higher values of resistivity, and the most of the part that is really, really low, almost 1 or 2 amperometers. Looking at the data of this piezometer that we have inside, the previous piezometer, we can correlate the two data, and we saw that the groundwater level was at 5 meters deep. That is the same depth of the boundary between the two zones. So the blue part is saturated, fully saturated, while the red part is almost dry. So the important part for the client was the dry part that he wanted to take under control during time. So what we did, and we are still doing, is to analyze the shallow part, the first 5 meters, and to analyze in time-lapse the evolution of the average resistivity. We have only 2 months of data, so now the situation, this purple line is really constant, that is good. Probably in the next time, this part will become more resistive due to the desaturation process. The last case, the platinum mine, in this case, the monitoring aim was the control of the seepage and saturation in the TSF dike. And also in this case, we performed some analysis on the average value of resistivity a long time, but in different layers, because the saturation is more layered. Here, just an idea of the fact that we can also control the quality of the data. So we can control the standard deviation of each measurement that is really good in the site, and also the RMS error of the inversion process directly on the platform. This is the situation in the site. We can recognize the layered structure. We can see a first layer that is high resistive because the soil was really, really dry, and we can encounter the high resistivities in the surface. Then until 5 meters, an intermediate layer, and between 5 and 10 meters, a zone that is probably partially saturated, while below 10 meters, really low values of resistivity corresponding to saturation. We also see that in the surface there is an anomaly, so probably a part with more saturation in the center of the profile we can identify. We don't have here a piezometer, so we cannot correlate the two data, but it would be great to have. In this case, we are analyzing time-lapse the evolution of resistivity in the shallow part. The resistivities are becoming they are increasing a long time because the shallow layer is really dry due to the high temperatures. Then the second part is the most important part because it is intermediate between the dry and saturated part, and it can be an interesting zone to monitor because the average resistivity values will indicate if the zone is getting saturated. So far, we have only 1 month of data. The situation is really constant. So just to conclude, geoelectrical measurements can provide useful information, and mainly used as a monitoring can be really useful to follow the processes underground. The Greta system is an effective and innovative solution and proved to be quite useful in many cases, in many TSF cases. Thank you very much. If you have any questions, comment, feedback, for me and for the company, it's really interesting to know the comments of people that are involved in TSF safety. And so here, now or also during the coffee break, please ask some questions. Thank you.
Thank you so much, Greta. I can say that it was very effective, as you said. So we could take questions from the audience first, and then we could move online. Could you help me pass that? Yeah. Could I have the other speakers also on the stage? You could go there.
Thank you for this interesting talks from all, Regula, Emanuele, and Greta. It's interesting. I have two questions. The first go to Regula because it's very relevant to what we are doing. Actually, we are combining NSAR with geotechnical design and analysis. We are using Sentinel-1 as well for practical projects where we monitor the displacement and soil moisture content. Sorry. We have been using it to calibrate actually the soil models for the creep, soft soil creep model for the beat in Netherlands, and also for the Northern double bower creep model for salt domes in Saudi Arabia. And I'm wondering if the same can be applied for North sand or sunny sand for tailing dam.
I'm not sure if I'm the correct person to answer this question. I think we have the Noorsand expert here somewhere. He was, yeah. So I don't know if it's possible with a short answer. If not, then maybe we can have a discussion afterwards in the coffee break and convey the answer to the audience afterwards. Yeah, I don't have, in other words, I don't have a short answer.
Awesome. I will catch later for sure. And the next question to Emanuele, I think you have shown that the accuracy for the failure prediction is still developing. But instead of getting a certain answer for the failure date, would it be possible to develop skeptability map that takes into account a range or a potential of the failure?
Okay, thanks for the question. In fact, there are some methods that, and probably that is the way. I'm not a big fan of deterministic predictions, and instead there are some ways to develop windows, and that's what we try to do also with Luca Picciullo. The problem remains. I mean, probably we are not able to give a definite prediction. We are maybe able to tell something is going on, and so be prepared, and so on. I think in this way you can put in place less heavy, let's say maybe there is no need to halt production completely. But again, the problem is, okay, then what do I have to do? So maybe I can increase monitoring, and so yes, probably I mean that is nowadays the solution, but maybe is not the solution that we aim to.
Do we have any other comments or questions?
I would like to follow on from this question about movements and predicting things to geomechanically. So my question is to both Regula and Emanuele, and it's about the Brumadinho failure, which both of you flagged up in your presentations. At Brumadinho, there are two hypotheses on the table. The panel said this was an ongoing geotechnical creep issue, and the presence of the drill rig was just accidental. The public prosecutor is saying the drill rig was key, and their view is supported by the people of Barcelona. So my question to you guys is, could you introduce the timeline of the drill rig's activities into your analysis and apply filtering to distinguish between these two competing views of the cause of failure?
I guess when, I don't recall exactly when the drill rig got in place, because that's a bit key, because we really have very few data points, as we both showed, towards the tail of the event.
Yeah. I think the timeline is known because the drill rig was moving along installing wells, but the particular failure coincided with the activities of the drill rig at that particular point of failure. So we, just on a simple Bayesian idea, you would say the failure occurs exactly under the drill rig and exactly at the time the drill rig is operating. You would say, well, actually, perhaps it has something to do with it, and it has nothing to do with ongoing geological processes. But they're not necessarily mutually exclusive propositions. You can still have ongoing processes, and then the drill rig does something else. But really, that's the key debate around Brumadinho is, was it caused by injecting groundwater or injecting drill water, or was it just merely an accident?
Yeah. Personally, I don't see how we should be able to split these two features in these few data points we have, but Emanuele has looked much more into exactly this time series. So,
in my point of view, that the methods that I showed at Foodzone site and others, they're like black box models, so they are based on the displacement, but they do not take into account what causes these displacements. And that is the problem. In some cases, also with not just tailings damming, but in some cases it may be explosions in open pit mines. It can be the type of the material and so on. So there is no way to put this into the model. The only thing that you can do is that when you monitor data and when you extrapolate time of failure, you are informed about what is going on, and you can use this information to help you to give significance to the results. And so when I said before about the reliability and confidence of predictions, there are some we can measure it in some ways, but the most important use that you can make of this information is to use it qualitatively to know that the prediction that you are giving probably is good, maybe because you know that there is something going on, and you know that this can be the trigger. But apart from this, I don't know of a way to introduce these analytically into these models, which are basically, like I said, black box.
The thought going through my head was you had some jumpy data, and I wonder if you put the timeline of drilling activities and then did something like a Bayesian updating, whether you might say, the spikes I have in the data correspond to when we have activity. So that's really my question, is could you incorporate some sort of Bayesian updating with point markers in time for when we have man-made activities?
Yeah, that is exactly what I meant. That is a pretty good example of what you could do. But it's something that you do with your own expert judgment. Yeah.
Suzanne? And then I come to you, Dipankar. Oh. There you go.
Thank you. I had the question for Regula, but perhaps a comment on the previous questions. It could be both. If the factor safety was already marginally low, was 103 or 105, then inserting the drilling water might have tipped the balance. We have cases like that for our quick clay failures in Norway, that the factor safety is so low to begin with, just having a snowy winter and having the snow melt will cause a failure. But my question to Regula is, you showed a slide where there were some red lines where you were detecting erosion. I don't remember exactly the technique. And my question is, could we also detect erosion underground in some manner with one of the techniques?
With geoelectric, yeah.
And would that also be applicable to ordinary water returning dams?
Maybe I could just first answer with the remote sensing methods I presented. The answer would be no, unless the erosion on the ground would lead to some kind of manifestation on the surface. Because we always we were restricted to the surface. So everything happening in the ground needs to transfer itself to the surface before we can see it. But
Yeah, I think
she
that
should be able to see
yeah,
it.
the main differences between this kind of methods and other kind of geophysical methods, such as ERT, is that these methods are related to displacements. So you have to start seeing something on the surface, and probably it's too late, I don't know. While in this case, you can follow the processes underground. So before they manifest on the surface. The other difference is that this kind of methods can monitor a really wide area, so mainly all the tailings dams. In this case, you have to select some parts, the critical parts.
That was the point of my question, is maybe if I could use your technology, Regula, to tell me where I should look for internal erosion. But that's also for tailings dam. You can have internal erosion. But okay, that's not possible today. Maybe something to work on.
Yeah. No, but I think you touch an important point. I think that remote sensing is often, I think in my view, it's exactly a method to highlight the hotspots or potential hotspots, and then go in with other type of measurements. Because you have, as Greta pointed out, you have this possibility for large area monitoring with restrictions. But yeah.
Yeah, first of all, excellent presentation by all the three speakers about the monitoring. My specific comment is for Emanuele regarding the observation, which you mentioned that probably the reason is not known when it is the deceleration, why still it failed, essentially. I guess every phenomenon can be explained through mechanics or physics. So have you tried to think from the fundamental mechanics if it proves whether there is a drastic change in the acceleration or deceleration, the rate of change, essentially del A by del T, if it is beyond a threshold value, whether that is the reason, or from the energy conservation theory, when we say there is a drastic change from kinetic energy to potential energy, have you thought from explaining the reason of the failure from the monitoring data, if it explains such kind of behavior?
Okay. We still did not make a modeling of the design because we focus just on, at the moment, on remote sensing. So actually our information about the tailings dam are from literature about the composition and so on. But I think that would be the next step because, of course, it tells us that we see half of the picture if we only look at the monitoring. But when I mentioned in one of my first slides the early warning systems, and next to forecasting there was monitoring, but there was also design, geological knowledge, and of course, so this part is also important. And so definitely it's going something that we will have to do for research, but for the owners of the tailings dam, I think that these two knowledges need to be integrated since the beginning, of course. Thank you.
I have some questions online, or do you want to go there, Luca?
I just want to add a comment on that. I was thinking about that actually, because we have seen the tailings dam in South Africa, how the displacement was going down, up, and then kind of steady situation, and how it's important data sharing, in this case, in situ data sharing, because this can lead to some considerations that can be important. You know, they can shed some lights on the reason why we see that type of thing, right? So that's the thing that maybe it's that part of the chain that is missing between what we see from the top of the dam and with the data that are available on the dam. Well, sometimes are not data available. That's the other issue, actually. Yeah, this was my comment.
So we have a comment from Maral, all the way from Mongolia. So the first question she has is for Regula. So she says, what are your thoughts on the applicability of large-scale, continental-scale INSAR processing to TSFs, such as the European Ground Motion Service INSAR?
I guess the question is kind of if it can be, if it's of any use.
Yeah.
Yeah, so again, I'd say for a hotspot analysis, it should be useful. NGI is actually part of the validation team of the EGMS, of this new forthcoming European ground motion service. And of course, with such really, I wouldn't say it's global, but it's large-scale continental services. You have some restrictions. When it comes to the EGMS, it's of course the resolution that can be provided, because you have zillions of data points and you need some servers that can handle that. So we have not tailing dams, but we have some of the validation sites are on waste sites, waste dumps. And yeah, I would say yes, as a hotspot identification. To go into more details, I think you need more local processings. You can still do that with the free Sentinel data, but more tailored to your sites.
If I may add something just about
sure.
it. We have tried to make some experiments with EGMS with pre-failure data, but data are elaborated so that we are not able to detect pre-failure images, because the example I showed before, the interference have been calculated all using images before the failure, but after the failure you have a loss of coherence, and that it makes data not useful. And EGMS are elaborated in such a way that you have all the data set, not just pre-failure. And so if there are some accelerations, it is possible you don't see them with the EGMS. So you only see that like the background deformation. So that is to keep in mind when one looks into EGMS data.
The following question is for you. So how do we differentiate the deformation due to the initiation of failure versus other activities upstream of the TSF, such as buttress construction?
Okay, the short answer is that you do not differentiate, but in general, in theory, but as it was noted before, if you have a knowledge of what is going on, this is something that you could qualitatively use as an input in your model, and so you know that you have to dismiss this because you know something. Another way is that in some cases, if the accelerations are not really power law accelerations, because tertiary creep is a power law acceleration. In other cases, you have smaller accelerations, like changes of trend. And in those cases, you see if you apply the forecasting methods, like in the last demos, you do not obtain anything meaningful. And so, but this works for most of the accelerations, but there are some accelerations that really look like something is going to fail. But they are not. Ultimately, nothing happens. And these are the problem. And at the moment, I think this is one of the one of the cutting-edge problems that we have now.
I think the last question is for Greta. So I think it's an interesting one. I understand how resistivity aids in distinguishing saturated versus unsaturated, but can you please further explain how would it help you to identify seepage through the wall?
Okay. The key fact is that you are measuring this section also twice per day, 3 times per day. You can decide. So a strong method that you can apply is to compare the different images that are not images, are data points a long time, and you can underline if a single part of the monitoring area is changing and the other not. We experienced a lot with river levees that are different from TSF, but some processes are the same. So for example, concentrated seepage, we could understand really well the exact position and depth and evolution of the concentrated seepage in the exact point, comparing the different data a long time.
I just had one. Oh, okay, we have a question from Ramon there. Could the last person who had the microphone pass? Oh, that's Luca.
Thank you. My point is about the prediction of brittle failure. I think we should distinguish between brittle failure and ductile failure. This is very important because people may believe that brittle failure can be predicted. My impression is it's not possible by definition of a brittle failure. So there is no signal, nothing happened. So you have a very marginal safety factor in a dam. We expect, or we may have a static liquefaction. Maybe there is nothing at all until the triggering happened. Something triggered the failure. That's my point.
Okay.
I'm afraid that people may believe now that we can predict that. So people can stay with a dam that is very unsafe because they are doing some very good monitoring.
Okay.
So I understand a very nice presentation. I love all your presentation, very good. But I'm afraid of that.
Okay, yeah, well, I didn't think that I was too optimistic, and you're right. There are cases that when you are not able to predict. I had an interesting conversation about this with Aldrich Hangre, and who said that in many cases the problem with brittleness is just a problem of acquisition frequency. Theoretically, before a brittle failure, maybe you have moments of creep deformation, maybe seconds or maybe minutes. But in some cases, yeah, in some cases, yeah, okay, exactly. Exactly. In some cases, there are. We have made a paper about open pit mine in Norway with very strong and brittle rocks, and in those cases, there was a G-beam SAR that was able to detect precursors lasting just few hours. But these few hours, 10 years ago or 12 years ago, they would have been considered a brittle failure. Now it is possible to predict them. In some cases, still, as I said, this brittleness, this brittle behavior is so short that it is basically impossible. So you're right. But I think this is a continuum. There is no brittle, and then there is, the creep, more plastic behavior that you are able to detect. It is a continuum. So in some cases, this range is long enough that allows us to make predictions. In other cases, like for example, think of a small rockfall of stone large like this that detaches instantly. Of course, it's impossible to make a prediction because maybe you have instance of creep before that. So I agree with you, of course. I'm not so tranchant between distinguishing two words, but of course, there are many, many cases where basically you cannot do anything about that. Yeah.
I had a question for Greta. So do you also assist like your clients to kind of identify where you actually are supposed to place your Greta sensors, or they have to pick? So I think that the niche is basically to identify where you should actually kind of install them to have them capture what we are actually looking for.
We are technology providers and not consultants, but obviously we can assist. We assist the clients or the consultants of the client to with some suggestions of some processes that the system can identify. But obviously the last word is to consultants and the mining company to identify the critical part. With our clients, they often they present us, we know these critical points, we already know that there are some problems, we don't know how to monitor, and so then we can configure the installation together.
So in using your technology, have you ever kind of had this encounters where you identify a weak zone or a cavity, because you spoke about saturation and unsaturation, but have you ever encountered where you kind of spotted a weak zone, or because you said that you could actually capture cavities or like some discrepancies? So
yeah, we had a lot of experience also in other kind of embankments, and we could identify concentrated seepages or under seepages. In that cases, the situation is stable. We could relate the groundwater table with the piezometers and also place show the situation, because sometimes it is not still so clear to the clients, so they know something, they don't know much data of the storing facilities, so we can have like a picture of the underground. But in this case, the situation is stable, so we didn't encounter any big problems so far. They are quite recent installations, so we are going on.
So if there are no more questions, I think we can. Oh, you had a question?
Yeah, I had one.
Okay, I thought you, yeah, sorry.
But first, I also would like to thank Ramon for his very important point. And I think it goes a little bit back to my second point of the conclusions, which I tried to kind of make a point that, yeah, we have all these methods now, but you need to know where and when to apply it. But I see that maybe we should work even better on a disclaimer. So I take that home. But I would still dive a little bit more into the technicalities of your question, because to me it seemed that the profiles that you showed, they were all inverted with the same method. So I was wondering if there is the possibility in the system to either use different arrays, you know, Schlumberger, Wenner, or whatever, and also to use different inversion methods, or is it just kind of you provide one type of inversion? Because, I mean, different inversions show different things.
Okay. Speaking about the electrode configuration, it is fixed, it is Wenner.
Yeah.
We tried different electrode configurations, but the one that works better with three-dimensional structures, such as dams or levees, is the Wenner, that has a high signal-to-noise ratio and also less three-dimensional effects. So we have this Wenner configuration array. Speaking about the inversion method, we have this algorithm with parameters that can be changed by the user. And also now we are implementing the time-lapse inversion. Yeah. Another thing really important is that you can extract all the data also to other softwares. So if you want, you can extract and invert with your own software.
Okay. Thanks.
Great. So we call it a session, and we probably would meet in another 20 minutes for the next session. So enjoy your coffee break. Hi. So hope you had a good coffee break, and we continuing with our next session, which I could probably call the French folk session. Hopefully the session is not going to be in French, and it's going to be in English. So the session is titled Acid Mine Drainage and Environmental Issues. We have first in-house Jerome Jacob from BGRM France. He's a bioprocess engineer and a legacy site manager at BGRM with expertise in bioleaching, mine water treatment, and mine site valorization. So we keep the same rules that we let all the speakers finish, and then we have the questions at the end. The floor is yours.
Thank you. Okay, hello everyone. I will present you the development of a new mine water treatment process from the lab scale to the full scale plant operation. This work was done with my colleague Fabienne Battaglia-Brunet, who lead the lab test, and Dr. Emanuele Gesnek, who lead on the pilot plant phase, and I took over by the end of the pilot plant. So the mine site is Loperec, is in the west of Brittany. It's an gold ore deposit with arsenopyrite-rich quartz vein and iron calcium-rich chert hosted by acid volcanic rocks. Paragenesis include arsenopyrite, pyrite, pyrrhotite, chalcopyrite, sphalerite, and galena. The ore body is estimated to be 360,000 tons at 8 grams per ton of gold, which is about 3 tons of gold. Speaking of the mining works, exploration starts in 1985 and end in 1994. We digged a 140-meter long incline, and all this work was done by a private subsidiary of BGRM. But the ore body was deemed too small and too complex to exploit, so there were no exploitation. So from 1994, we start the closure of the mine site. And one of the main issues of this mine site is mine drainage. It's actually a neutral contaminated mine drainage with a pH ranging from 6 to 7, an average flow rate of 18 cubic meters per hour, very little dissolved oxygen, very steady temperature, obviously, and main contaminants are iron, arsenic, and manganese, with iron ranging from 2 to 20 milligrams per liter, arsenic up to 1,500 micrograms per liter, and manganese ranging from 500 to 1,500 micrograms per liter. So the mine drainage is coming out of the incline. So it's not a tailing dam, but we did, and we are still doing the same kind of work on seepage from a tailing dam. So 1994, start of the closure. You can see on this graph that arsenic and iron concentration are behaving in the same way, while manganese have a very different behavior. And all of these elements react differently to a rainfall event, but strongly with rainfall event. Arsenic speciation is important. On this mine site, we have mainly arsenic 3 most of the time. Around this time, after some heavy discussion and some internal conflict around the end of the 90s, we finally acknowledged that this water would have to be treated in order to get the relinquishment from the French state. And around the same time, around year 2000, BGRM found a bacterial arsenic oxidation. In water, arsenic exists mainly in two forms, arsenic 3, which form an extremely mobile neutral complex that does not bind to the solid, and arsenic 5 that form an anionic complex that can bind to many solids, especially iron oxyhydroxide. So if you got an arsenic 3 containing water, you need first to oxidize arsenic 3, then to sorb arsenic 5. BGRM found an arsenic 3 oxidation bacterial activity in another mine site, not this one. It was also a gold mine site with arsenic, which was called Cheney. And it was done during a BGRM-funded fundamental research project. The bacteria was named CAS01. It's an autotrophic bacteria using arsenic 3 as an energy source. So you don't need to feed the bacteria, it's autotrophic. It can feed by oxidizing arsenic. We started the lab test work in 2004. The goal was to see if we can use this bacterial activity to treat the water. So we wanted to assess the ability of bacteria to form a biofilm on a suitable support, because you need to have a lot of biomass into one reactor. And the other goal was to assess the capacity for continuous oxidation over the long time, because mine water will flow like this with such a contaminant for a long time. What we did are continuous tests in Puzzolana column in the lab with a synthetic entrant and with endogenous bacteria. So we, on this mine site, Loperec, we found another bacteria strain, different but related, and we choose to use these ones that were isolated. And for the lab test, we start with a residence time of 24 hours. A couple of months later, the column were moved on-site to use the real effluent. And this was done during a BGRM-funded research project. So here are the results of the lab-scale test. We did have the formation of biofilm and the total oxidation of arsenic 3 and total removal of arsenic 5 with iron hydroxide. And we succeed to decrease residence time from 24 hours to 4 hours. When the columns were moved on-site, we had two columns actually. One column with the biomass that was grown in the lab, and one fresh column with fresh pozzolana without bacteria. Because if you have a big biofilter, with several cubic meters of pozzolana, inoculation can be an issue. And if you have to prepare a special inoculum for your full-scale biofilter, it can be difficult. But we had a pretty good result, total removal of arsenic 3, near total removal of arsenic 5, and total oxidation of iron 2. And we had auto-inoculation of the column, of the fresh column with the mine water. So the bacteria, that's why we choose to work with the bacteria endogenous from this mine site, because we wanted to be as close as possible as the real condition. On the picture, you can see the bacteria on the pozzolana with the exopolymeric substance, which forms the biofilm. Then we did the pilot test. So the goal of the pilot test was to validate the process diagram under real condition and determine operating parameters: optimum residence time, system clogging, frequency, and method of pozzolana renewal. We did continuous tests in pozzolana biofilter on site with the real water. The main difference from the full-scale plant was residence time. In this pilot, we set the residence time. Most of the experiments were done with 1 hour of residence time, while on the full-scale plant, flow rate can range from, let's say, 10 to 70 cubic meters per hour. And your full-scale plant always have the same size. So residence time will change from factor 8. And it is at this stage that we add a settling tank before the biofilter to prevent clogging of the biofilter by iron precipitate. This first part of the pilot was done during a collaborative public-funded project funded by the National Research Agency, which was a COBIAS project. The first result of the pilot in 2008 and 2009 were not that good. We had an iron removal between 36 and 100%, and arsenic removal between 48 and 100%. This was mainly due to an insufficient oxygenation prior to the pilot plant. At this point, we had several issues. It was the end of the COBIAS project, so we had no more funding to progress in the process development. We had a huge funding conflict with the companies that did the mining works, the company who owned the mining license. They did not want to fund the process development. And in 2011, the administration set water quality threshold to this company. So we had to decrease iron concentration below 3 milligram per liter, arsenic below 100 microgram per liter, and manganese between 1,000 microgram per liter. It means that we start the lab test in 2004, and 7 years after, we only had the water quality threshold. It's very hard to develop a process when you don't know what are the objectives, what water quality you have to reach. But in France, it's not uncommon at all. It can be difficult, but we have to deal with that. And I should specify that it's site specific. So these thresholds are not the same for all mining sites in France. It's different for every mining site. With this new water quality threshold, the subsidiary agreed to fund the end of the process development. So this is the result from the 2011 and 2012 study. We had improved oxygenation of the water, and we had a very good removal of arsenic and iron below the threshold, and even manganese below the threshold. But as you can see, the threshold, it's a result of a negotiation between the company and the state, and the threshold for manganese is very close to the concentration in the water at the mine drainage spring. So now we wanted to implement the technology at full scale. It was difficult for us to find a competent design office to take on the project. We have a lack of consultancy which are good in mine water treatment in France, because the mining sector in France is just almost dead. And we wanted some company to implement our process. So that was not easier. Finally, we select Golder France with the support of Golder Canada. And at this stage, some shortcomings of the pilot study were revealed. We had a lack of information on the influence of residence time in the settling step. We had a lack of information on clogging time of the biofilter, because even after 2 years of pilot operation, there were still no sign of clogging. And we have a lack of information on sludge production in every step. So you can see here on the picture the final plant with the primary waterfall, 2 settling ponds in parallel, the secondary waterfall to oxygenize the water, and the 2 biofilters. We had some heavy discussion on design flow rate, because mine drainage average flow rate is 18 cubic meter per hour, but maximum flow rate is 74 cubic meter per hour. So BGRM proposed to set design flow rate at 40 cubic meter per hour, which is like 90% of the time. But Golder insists on setting the design flow rate higher at 60 cubic meter per hour, which is 99% of the time, more than enough. But the main reason was Golder was not that confident in BGRM process, and they wanted to oversize a bit the treatment plant to be sure to reach the water quality threshold. Final sizing of the plant, we have 2 settling ponds of 300 cubic meter, 2 biofilters of 30 cubic meter, and a 35 meter long grid bed. And this is fully passive. We don't use electricity at all. Water flow with gravity. We don't use chemical, and we have very low maintenance. There is someone on site half a day a month. And from the plant started to operate in 2017, and we still have not dislodged the settling pond. We don't need to. So very low maintenance. When we start the plant, we did a pretty serious study of the behavior. We have very good removal of arsenic, iron, and manganese. It was expected, but it took 40 days to achieve a good manganese removal efficiency. This is because at first, manganese oxidation is catalyzed by bacteria, so you need to wait for the biomass to grow. Once bacteria are oxidizing and precipitating enough manganese oxide, we have an autocatalytic effect. Manganese oxidation is catalyzed by manganese oxide. So once it has started, it works really well. But we had a very huge surprise, which is the biofilters were built to remove arsenic and manganese, and arsenic were always removed in the settling pond. The first year, we studied the plant as it was, with the 2 settling ponds and the 2 biofilters. But we wanted to see what was going on at design flow rate. So we choose to change water flow to use only 1 settling pond and 1 biofilter. So we decrease residence time pretty strongly. But even in this condition, we have very good removal of arsenic, iron, and manganese, and arsenic stay removed in the settling pond, not in the biofilter as expected. So we are now in 30 years of closure. We did 10 years of research and development, but we still had some surprise at the end of the day. So it's very bad to have a surprise only in your full-scale plant. It was a good surprise because arsenic is removed a bit earlier than expected, but still we did not like that. It was a very rare and precious opportunity to follow a process from the lab scale to the full-scale operation. And it's very rich in information. And when you are designing your lab scale test, if you know what will happen, what can happen in pilot test and in full-scale operation, there are some new issues you are thinking about from the start. It was very difficult to fund this research process. We had to rely on a public funding research. Relinquishment and transfer of the mining site to the state is expected at the beginning of 2024. And when this will happen, the company will pay for 10 years of water treatment operative cost. That's all. Thank you, everyone.
Thank you for the nice talk. It's nice to actually see the development of something from a lab scale to actually being implemented on the field. That's very rare. And moving on to our next speaker, which is Gabrielle Dublet-Adli. She's also with us at NGI, and she has a vast research experience from Stanford and EPFL, and she uses her experience for advising on metal contamination in soils, sediments, fly ash, acid mine drainage, water, and snow. So the floor is yours.
Yes, and I will also talk about about mine drainage. Here it's acid mine drainage, and it will not be about water treatment, but about preventing the drainage to happen. And the results I will present in this talk, they were obtained in a study that was done by several collaborators, including Thomas Pabst, who will present later. So just to put a bit of context of acid mine drainage in a tailing dam, here is an example, a famous example in California, where acid mine drainage was causing environmental problems and remediation solutions were found. But now I want to talk about, and acid mine drainage, what's the process? What are we talking about? So it's when you have sulfide containing tailings, the sulfides, like for example here it's pyrite. It's reacting with water and air, like an oxidant. And then the oxidation process releases acidity and heavy metals or contaminants in the water. I will explain it a bit further later, but here is a case of acid mine drainage we have in Norway. And in this case, it's an old mine that is not in use anymore. So the tailings are weathered. And there the acid mine drainage has a pH of 2 to 4, so it's very acidic, and it causes copper contamination in the river downstream. And what's the process of sulfide oxidation? I'm explaining the reaction now because I will use it in the talk. I will use the equation, but what is important is the things that are in this equation. So we oxidize sulfides, like here it's pyrite. We oxidize it with oxygen and water. So oxygen is the blue and water. And then we produce the acidity, it's the protons on the right. And it also produces iron 2, which is then oxidized, and that's leading to iron 3 minerals precipitation. That's what gives the orange color in the water. Okay, so that's oxidizing. And then Jerome talked a lot about bacteria. So when you have bacteria in the system, it increases the rates of the iron 2 oxidation to iron 3. So this is the process. And by understanding this process of acid mine drainage production, we can understand how to prevent that. So different approaches to manage acid mine drainage risks. It can be to treat the water, like we had the talk before, or it can be to prevent contact of the tailings with water, for example, with water impermeable covers. Or it can be preventing remove the sulfides so that they don't produce acid mine drainage, or remove bacteria, or remove oxygen. So using, for example, there are different types of oxygen barriers. Oh, this is going very fast. Okay. Here. And one example of oxygen barrier I'm talking about now is the cover with capillary barrier effects. So here we use the principle that oxygen diffuses slower in water. So we have a water retention layer here, a moisture retention layer that is sandwiched in between two layers of coarser materials. And then the oxygen is diffusing slower, and it doesn't produce as much acid mine drainage. But so in these covers with capillary barrier effects, it was proven to be efficient at limiting the production of acid mine drainage, especially in fresh tailings. So we have some typical criteria to assess the performance of these covers. Its water saturation should be higher than 85%, and oxygen flux should be lower than 50 grams of oxygen per meter square per year. So we have criteria designed for fresh tailings. And what is fresh tailing versus old tailing, maybe? So here you see the rate of acid generation over time, and you see that there is a lag period here where the acid is not generated. So here I would say the tailings are fresh. And then when the acid generation has started already, you have accumulation of oxidation products. I showed the reaction before, and this orange color, that's the precipitation of oxidation products. And then you have these oxidation products here. So the question is, the oxygen barrier that was designed for fresh tailings, does it function also for old tailings when you have already the oxidation products formed? So there was column tests with sulfide-containing tailings that was covered with an oxygen barrier with a moisture retention layer. And we tested two different types of materials for this moisture retention layer. One was fine sand, and one was a material found close by, so a low sulfide tailing. So one that was already weathered for a long time, and there was no sulfide anymore. And then the oxygen and water conditions were monitored in this column, and the leachate was collected out of the column. So the water was poured on the top and going through and collected at the bottom and analyzed over time. So first, I said that the principle of this oxygen barrier is that we have a moisture retention layer. And so the first thing to assess the performance of the cover is to see if the materials were able to maintain the water over time. So it was saturated continuously. So the properties of the materials used were suited because, so here is the core sand that was used to sandwich the moisture retention layer. So sorry for the pointer, it's difficult to control, but here is the core sand. So it's really contrasted grain size compared to the moisture retention layer in here. And also we have well-contrasted degrees, water retention properties. So the material properties were suited, and actually here it's the degree of saturation that was followed over time. And you see the saturation in the cover layer. It's in here. It's the two materials tested as a water retention layer. The saturation was kept above the criterion set of 85% saturation. So that means that the cover was efficient at retaining water, and so it was complying with the criterion set for fresh tailings. Here you see the degree of saturation in the materials above and under the tailing. Yeah. So it was a good material. It was a good moisture retention layer. So the cover functioned. However, it didn't function very well for solving our problem of acid generation. So in red here, it's the pH over time in the control column with only the sulfide-rich tailing. And the blue and orange lines, it's the pH out of the covered columns. So after some time of equilibration, it was a bit higher than in the control column, but still very low, like pH 2.5. It's not what you would like. And interestingly, if you look at the gray line, so here it's the control column with only the sulfide poor tailing, like the one used in the cover material. that's not supposed to contain sulfides, the pH is also very low, like 2.5. And in this one, it's a lot of iron oxides, it's a lot of jarosite. And the hypothesis made here is that the pH is actually maintained acidic, partly because of the occurrence of these secondary minerals, iron-3 oxide minerals, which in water lead to production of acidity. Yes, so that's one process observed, and the other thing is that you could say, okay, maybe the pyrite oxidation is still limited by the oxidation, oxygen barrier, but it was not very efficient either for that. Here you see the concentration of iron and sulfur over time. In red is in the control column, and the orange and blue lines is in the covered columns. So the iron and sulfur were reduced. I mean, the concentrations were lower in the covered columns, but only half about. So that means that pyrite oxidation was still going on. And a hypothesis made here is that the occurrence of these iron-3 oxidation products, it was a source of iron-3. At low pH, the iron-3 is mobilized. And then, so this is the iron-3 oxidation products. They release iron-3, and the iron-3 is catalyzing the oxidation of pyrite, even without oxygen. Here you don't have any oxygen involved. But at acidic pH, the iron-3 ions are catalyzing the oxidation of pyrite and produce acidity. So here we have two ways the iron oxide minerals control the acid mine drainage production. It's first by indirect oxidation without oxygen, and also because the jarosite in water leads to acidity. So then it's very important to understand what are these iron oxide minerals and how is this iron-3 available. Because the availability and the reactivity of these iron-3 minerals will depend on their nature, their crystallinity. And with XRD, so with X-ray diffraction, we only identified some jarosite. And we identified some jarosite, so you see the here, sorry for the pointer. But it was a lot of iron and sulfur that was not accounted for in these XRD results. So that means that there are some iron-3 minerals that are not seen with XRD, probably because they are not crystalline. So to identify these not crystalline iron-3 minerals, we used another approach, which is spectroscopic, and which is using absorption of X-rays by the material at the edge, like the energy of iron absorption. And so you get different types of spectra for different types of iron-3 minerals, or iron minerals, sorry. So anything that contains, so the iron is giving a signal, and depending on where it's, in which mineral it is, it will give a different signal. So here it's signatures of different minerals, and we use linear combination fits of the signature of our two tailings to estimate the proportion of iron that was in these different phases. And so in this tailing, that is the one we tested in the columns, most of the iron was in pyrite, and we saw some jarosite, like we detected with the XRD, but we also have some in ferrihydrite, which is the amorphous iron-3 oxide. So that's probably an additional source of iron-3 that is rather available for being in solution. And in the covering material, there was also a lot of iron-3 minerals that were not detected by XRD. So here, what I want to conclude with is that it's a big difference if we cover the tailings when they are fresh versus when the oxidation has already happened. So yeah, the time is important. And when we cover tailings that are old, for example, it's a legacy site, or yeah, it's already weathered, then like Jerome talked about how to treat the acid mine drainage. So it's important to treat it for as long as needed, and it can be a long time. Here in blue, it's the release of acid mine drainage over time, and the release of it can last longer than the production of acid mine drainage in the masses. So now the next question is, if you cover the masses, it will probably help for limiting the oxidation of sulfides, but some acid mine drainage will still be produced. And for how long will it be produced? This is an important question for knowing how long the drainage should be treated. And this is a knowledge gap we have still. And this study, so the covers with capillary barrier effects, normally they are performant for limiting acid mine drainage production from fresh tailings. So this is because the criteria for designing the covers and for for assessing the performance of the covers, these criteria were defined for fresh tailings. So now it's important to also revise these criteria in case of weathered tailings. And that's what I wanted to say. Thank you.
Thank you, Gabrielle, for the interesting talk. I think it's a very important discussion, especially when you're talking about closure of dams. And I think we need to focus a bit more on understand these processes much better. So moving on to the next speaker. So we have Thomas Pabst, who is a fresh import from the Polytechnique Montreal to NGI. And he specializes in geotechnical and mining engineering with a focus on mine waste management and reclamation. So the floor is yours.
Thank you very much for the introduction. Hello, everyone. So I'm going to present today some of the recent results we have obtained regarding the development of new technologies, new approaches to manage mine waste. So what are we talking about here? We are talking about solutions to the three main problems that we have been dealing with for the last 2 days. The first one, of course, is the continuous and significant increase in mine waste production due to mainly two factors. The first one being the general decrease of the ore grade internationally, and secondly, the significant increase of needs in raw materials to produce the equipment we need for our development. So we are producing more and more mine waste, and this waste, unfortunately, often contains sulfides, which can react with water and oxygen, as Gabrielle has just mentioned, and produce acid mine drainage. So of course we can treat the acid mine drainage, but water treatment is necessary but not sustainable, because acid mine drainage generation can go on and on for hundreds and thousands of years. So what we do usually is that we try to prevent the contamination at the source by preventing the reaction to occur, and for that we build engineered cover systems. And recent research, for the last 10 or 20 years, have worked a lot to propose solutions. And we now have many techniques, for instance, the water covers, the cover with capillary barrier effects that was mentioned before, the elevated water table with monolayer cover, which all work very well. The problem is that we have so huge mine waste storage facilities that we need more and more materials to build these cover systems. So that's a big challenge, because we need to find these natural and clean materials. And the third problem we have, of course, is the geotechnical instabilities of mine waste. We have had many cases of failures showing that even though we have improved our understanding and our technology to dispose of tailings, we still have these events which happen. And one of the reasons for this is often the very high water content of the tailings. And then we pinpoint one of the main problems we have, is that the solutions to each of these problems can be contradictory. For instance, if we want to reduce the risk for geotechnical instabilities, we need to decrease the water content. But by doing so, we also increase the risk for geochemical stability. So it's not always easy to find solutions to all these problems at once. And that's what we try to solve by developing these integrated mine waste management technologies. Integrated mine waste management tries to find solutions to tackle the different problems at once. So instead of waiting for the closure to think about reclamation, we try to integrate reclamation in the development of the mine and the production processes. For example, instead of proposing environmental solutions which actually decrease the geotechnical stability, we try to find solutions which can at the same time reduce the risks for geotechnical and geochemical instabilities, and so on. So integrated mine waste management is actually directly linked with these concepts that are very important for today's mining industry, which are the resilience, which is the sustainability, the planning, and so on. Finally, integrated mine waste management has no clear definition, but should be seen as a toolbox which contains a lot of different approaches. There is not one technique which is magically functioning for all the cases. These techniques have to be adapted to each specific situation, but we have all these techniques that have been developed over the last few years. So today, I will not have the time to go through all these techniques, of course, but I would like to focus on 3 of them. And maybe starting with the most logical one, which is the co-disposal. So far, what we have been doing is to dispose of waste rock in piles and tailings in impoundments. But when we look at the properties of these materials, why not trying to get the best of the two? The waste rock has very low and poor hydrogeological properties, but has a very large strength. To the contrary, the tailings have very good hydrogeological properties, but so especially the water retention capacity, but they are very weak, low strength, and very slow consolidation. So instead of disposing of them in different sites, can we actually dispose them at the same place and get the better of the two worlds? So the first idea, of course, is to mix them directly, and by doing so, researchers have shown that we actually get the mechanical properties of waste rock and the hydrogeological properties of tailings, which is exactly what we need, what we're looking for. Of course, it's not that easy. We need to conduct laboratory tests and field tests to find the right ratio of mixing. Otherwise, a small change in the ratio may actually decrease the properties we are looking for. We have also tried to implement this in the field. It works well. We are able to mix the material in pretty large quantities, but we are still facing the problem of the very large blocks. And also, this technique of mixing is not applicable for huge sites, so it's good to prepare small amounts of materials, which may actually be used for very specific purposes on the mine site, like, for instance, reclamation. So we have also proposed another technique of co-disposal, which is the concept of waste rock inclusions. So waste rock inclusions consist actually in building pathways, linear drainage systems within the tailings impoundment. So the objective of these waste rock inclusions is first to accelerate the consolidation of the tailings by reducing the distance for the excess water pressure to dissipate. Waste rock inclusions can also significantly improve the static and dynamic stability of the tailings storage facilities. It also helps to compartmentalize the TSF, so that if we have a dam failure, there will not be that much amount of tailings flowing to the environment. So we reduce the consequences of the dam failure. And also, it facilitates the management of the tailings because it provides roads for the trucks to circulate on the site. So you may actually look at that as a very theoretical solution, but it has been implemented on several mine sites, especially on the Canadian Malartic mine site, which is the biggest open pit gold mine in North America, with pretty good success. So I will not have the time here to present you all the results and all the research that was conducted to show that this is a solution which actually works, but just to mention a few verifications that we have done, a few studies. First, we have shown that these waste rock inclusions do indeed increase the stability of the dams by significantly increasing the factor of safety of an upstream dam and also other types of configurations. We have also, more importantly, shown that waste rock inclusion can help strengthen the tailings dam so that it resists much better the effect of an earthquake. So for instance, here you have the results of simulations conducted with FLAG2D with dynamic loading, simulating a typical earthquake from the east coast of North America. And you see that without an inclusion, typically what happens is that the tailings RU goes to 1 and we have liquefaction leading to the failure. But if we install waste rock inclusions, we keep the RU well below 1. We have no liquefaction and we have displacements which do not exceed a few dozen centimeters. So we can keep our infrastructure. So when building such waste rock inclusions, also one of the questions we may have is that what happens in practice during the construction? Because this waste rock inclusion will be built during the deposition of the tailings. And as you can expect, there might be some intrusion of fine-grained tailings within the coarse waste rock inclusion. So we have conducted some field tests by digging up some trenches in the inclusions, and indeed we observed some mixing and transition zones between the tailings and the waste rock where we had a mix of the two materials. So the question is, does it affect the performance of the waste rock inclusion? So we have complemented this analysis by laboratory tests, where we have been testing different waste rock types, the waste rock particle sizes, different tailings, also different hydraulic gradients, and different water content for the tailings. And what we have observed is that at worst, the maximum retention of tailings within the waste rocks does not exceed around 20%. And by conducting also permeability tests, we have shown that even though we have 20% retention of tailings, the hydraulic conductivity of the inclusion of the waste rock is not decreased by more than 1 order of magnitude. So we have an effect of the intrusion of tailings in waste rock inclusions, but it does not significantly decrease the performance of the drainage system. The final point I wanted to discuss today about waste rock inclusions is the geometry of the system. So as you've seen on the picture, what we suggest is to use waste rock inclusions which are parallel to the dams and which are actually placed regularly from the dam. So this was based on the parametric optimization of the behavior of these waste rock inclusions, but it was also complemented and validated by using topological optimization. So topological optimization is very interesting because it has no geometric criteria, predefined criteria. So it really gives you the best theoretical solution. So sometimes it's not applicable, but in that case, what it showed us was that this design with parallel waste rock inclusions was actually the optimum design. So that's one technique in our toolbox. The second technique I wanted to discuss today was actually the backfilling, not the underground backfilling, because that has been used for over 30 years in the mining industry. We have a very good control of that. But I wanted to talk about pit backfilling. So pit backfilling has also been employed, and it has many advantages. The main advantage is that we reduce completely the risk for dam failure, because we have a structure which is underground, so we have no risk of having tailings flowing to the environment. However, despite these many advantages, one of the main risks or problems or question we have is actually that tailings are disposed of in the pit directly in contact with the groundwater. So if the tailings or the waste rock which are backfilled are contaminated, there is a risk for actually to have some contamination of the environment. So what can we do to avoid this risk of contamination or to limit this risk of contamination? Again, the solution may actually be in the co-disposal. So to actually improve the environmental stability of backfilled pits, we have proposed this, improved the concept of the pervious envelope. So the pervious envelope is actually aiming to create some permeable surrounding around the backfilled materials so that the water from the groundwater is actually following this path and not crossing and not being in contact with the potentially contaminating mine waste. So this technique has been developed in the years 2000, but because of the limitations of the computational systems were difficult to prove. So we have been conducting new simulations using the nowadays capability of our computers by conducting very large simulations with over 20 million elements using discrete element methods and also finite element models. And we have actually shown that, yes, the pervious envelope works very well if we can assure that this pervious envelope is at least 100 times more permeable than the waste that we dispose of in the pit. So how do we build in practice this pervious envelope? Well, the first idea would be to use the natural rock, because we know that when we produce ore from a pit, we blast quite heavily the rock, and we actually increase locally for over a few meters around the pit the permeability. So we have been conducting numerical simulations, and especially stochastic simulations, where we actually made all the parameters of the cracks and the fractures change at the same time. So that's a bit different from a typical sensitivity analysis, where we just change one parameter at a time. Here we were changing all of them at the same time. And based on that, we were able to observe that this criteria that we call the DFI, which is the derivation factor index, which is actually a sort of estimation of the efficiency of the pervious envelope, was varying a lot depending on the type of waste and type of rock where we were disposing of our mine waste. Basically, we will show that in blue, when we dispose of waste rock, it's difficult to get a pervious envelope from the blast damage zone, but when we have fine-grained tailings, it may be much more efficient. So what do we do when the rock cannot be used as the pervious envelope? Well, in that case, we need actually to build it. And for that, we need to use a very permeable material, which can be, of course, waste rock. So we can actually build this pervious envelope using non-reactive waste rock, and it works very well to divert over 99% in the best situation of the groundwater flow. We have used topological optimization one more time to show that this pervious envelope was the most efficient and optimum design for circular pits. In the case of a more elongated pit, we showed actually that it could be beneficial to also have some inclusions or drainage paths within the pit and parallel to the general groundwater flow. And in that case, we actually also decrease significantly the contact between the groundwater and the backfilled mine waste. So 2 more comments about this pervious envelope. So the first thing is that you see that the design is kind of similar to the waste rock inclusion as I mentioned before. And actually, we have tried to look at how they can contribute to accelerate the consolidation of tailings disposed of in the pits. That's very important because if we use these waste rock inclusions or this pervious envelope made of waste rock, we also decrease the available volume for tailings. So is it possible to compensate this volume loss by accelerating the consolidation and at the end of the operation having a few dozen meters more on the top to dispose of more tailings? So we have been conducted simulations also in association with our mining partners, and we have tried to see what was the best configuration to accelerate the consolidation and to actually get more volume to dispose of our tailings at the top of the pit. And final point is about the application, about the operationalization of such technique. Because all of this, as I mentioned several times, was developed using numerical simulations. So now how do we actually build this pervious envelope using waste rock in the field? The thing is that it's not so easy, it may be also quite costly, especially if we want to dispose of the waste rock from the surface of the pit, especially when it's very deep. So we were very lucky because some of our partners had started actually to dispose of waste rock in their pits, so we are able to use this information to actually better understand what was happening with our waste rock. So what we did was discrete element models calibrated on laboratory and field tests. As you can see here, we have used spheres to simulate the waste rock blocks, which may be unrealistic at first, but which are actually controlled by two main parameters, the rolling resistance and the friction coefficient. And we have proposed also a technique that was published to actually calibrate these two parameters based on the laboratory test and the field test to make sure that these spheres, which are a simplification of the reality, do actually represent the real behavior of waste rock. So we compared our numerical simulations, we validated them with field and laboratory results, and it functioned very well. We had a very good agreement between the two, and based on that, we were able to test different deposition conditions. How much waste rock, maximum particle size, the height also of the deposition, the strategy for lateral deposition and so on, and to propose some recommendations to actually improve the deposition of waste rock and to prevent as much as possible the segregation of the particles. Finally, and I will go a bit faster on that, last point is about the dewatering. So we have discussed a lot about the risk for liquefaction. One of the techniques that we can use to reduce the geotechnical risk of tailings is actually to remove the water from them so that we increase their strength. There are different steps, and the driest tailings we can achieve is actually called the filtered tailings. So filtered tailings are produced in filters. We produce a filter cake and we can just transport it by truck and also then compact it in the TSF. It's very efficient. We have very low risk of liquefaction, and also we do not need to build dams, so that actually it compensates the fact that this technique is more expensive, but overall it's less expensive than at the end of the operations than a typical slurry TSF. We have two problems with filter tailings. Of course, it's never that easy. We have some challenges. The first one being the increase of the water table due to the exposure to the environmental conditions. I will not talk about this. We still have research going on that topic. The second problem is that because the tailings are desaturated, they are also exposed more to oxidation and to acid manganese generation. So that's why this technique of filtration has been very little used for reactive tailings. So we conducted in the laboratory some experiments to evaluate the time for the acid generation to start, depending on the degree of saturation. And we have observed two very interesting things. First is that for most tailings, we can define what we call the critical degree of saturation. Above this value, we have little risk of acid mine drainage. Below this value, we will generate acid mine drainage. And we were also able to determine the critical time, which is actually the time that we can wait until acid mine drainage generation starts, if the degree of saturation is below the critical degree of saturation. So based on these two criteria, we have proposed two approaches for the mine site. First, to keep the degree of saturation above the critical degree of saturation, but we have shown using numerical simulations calibrated on laboratory tests that it was very difficult, even by taking into account climate change and increase of precipitation, to keep this very high degree of saturation. So this technique was a bit risky. So instead of that, we proposed another one, which consists in disposing new layers of tailings regularly at a time frame which is smaller than the critical time. And by doing so, we make sure that the tailings are never exposed more than their critical time, and so we can expect to avoid the generation of acid mine drainage. So we also have worked on the mixture of different types of tailings, working on tailings which are very acidic, acid generating, and some others which are also acid generating, but which have a higher buffer capacity. And we have shown, we have been able to produce some of these abacus, which are very useful in the field for mining companies. For instance, this one at the bottom showing what is the expected pH in the tailings, depending on the time of exposure, the mixing ratio, and the degree of saturation. And same thing for these two graphs. We show, for instance, if we take the final one here, we see that, for instance, if a mine site knows that they can dispose of a new layer of tailings because of their production rate every 3 months, then we go to here 100 days, and we see that we need at least 90% saturation, or we need a mixing ratio of 60%, 40%, things like this. So that's very useful in practice, and we have also been able to propose different techniques of deposition, layer by layer, small layers, thick layers, and so on, all need to actually decrease the risk for acid mine generation and still getting the good aspects of filtered tailings. So these were just a few of the many different techniques for integrated mine waste management. Time is flying, so I will move to my conclusion, which will be in 3 points. The first one is that the development of low-grade, large volumes mines force us to rethink the way we dispose of tailings and waste rock. We cannot just continue to do the same thing as we've done so far, just bigger impoundments, bigger TSF, and so on, because otherwise we will have more and more problems with bigger and bigger consequences. Second point is that, as you've seen in my presentation, it's very important to have a multidisciplinary approach that hydrogeologists, geochemists, and geotechnicians work together to propose the best solution to avoid these geochemical and geotechnical instabilities. And finally, even though I presented these techniques and I believe they are functioning well, we are still at the beginning. Integrated mine waste management is something that we have started to talk about maximum 10 years ago. So we still need some research to improve this technique and to think about new technologies to do even better. So thank you for your attention. I would like to finish my presentation by saying thanks also to the funding agencies and the mining partners which are financing the research institutes of mines and environment. Thank you, everyone.
Thank you very much, Thomas, for actually bringing up this important discussion that the geochemical stability and the geotechnical stability are coupled, and they often fail to communicate amongst each other. But this is something which needs to be addressed. So now the floor is open for questions. We have quite a lot of time, so I don't see any questions online, but I see that in the house we do have, I would request the other speakers too to be on the floor, but some of the attendees are here specifically for this session, so I would expect questions from their end. So.
Lunchtime is never a good time for questions.
Yes, wait, I could, where is the microphone? Is it here?
No.
Nope.
Oh, yeah.
There, Annika needs it, Luca.
Oh, yeah. Thanks for very interesting presentations, all three. My question is to Thomas. The waste rock inclusion in tailings dams, I thought I've never heard about it before, but looks very interesting. But I guess stability comes in as well if you do like high waste rock walls, so to say, in the impoundment, and the tailings around is very soft. And the position of tailings often take place from the dam crest, sort of from one side. Have you been looking at the stability issue? And I guess it's a case of how wide you need to do those and how high they need to be.
Yeah, so that's a good point. First, about the stability, it's important to remember that you don't build it at once. You build it progressively, and so you will have tailings on both sides. So stability will be ensured because of that. So even if it's soft, you will have the same pressure, the same stress from both sides. So that should not be a problem. Also, they are quite wide because they should allow the traffic on the surface. So we usually say that minimum 6, but usually around 10 meters wide at least, built progressively. So stability, also they are also funding on the base. They should be funding on the base of the TSF. So foundation should also be stable. Now, when it comes to the deposition from the crest, actually you create internal dams. So what will happen is that you will fill the TSF from also from the waste rock inclusions. So usually alternating from between the sides of the TSF.
There's a question behind.
Probably just following on from Annika's question, building the waste rock in the facility involves a lot of planning early on to start the waste rock before you even start depositing.
Sorry, can you just...
So build...
Thank you.
Yeah, following on from Annika's question, building the waste rock inside the facility involves planning from the start. Now, if you're at that stage and you're planning why you're building a dam, if you've got that rock fill, you should be just putting the rock fill on the downstream side and having no dam. As a more fundamental question of de-risking your facility in terms of stability. Rather than putting the waste rock in your facility and then building an upstream dam over the top of it, you could just use the rock fill to stabilise your structure in the first place.
I'm not sure to understand the point here. The thing is that, yeah, so of course you have to design this from the start of the operations. It's just that when you have so huge tailings storage facilities, it generally helps with the, it's just better actually in terms of management, in terms of stability. And also something that I didn't mention is that in the case of, for instance, an underground mine, you can actually completely remove the need for a separate waste rock pile. So because yeah, underground mine, you will be around 10% waste rock for 90% tailings. So in that case, you can just put all the waste rock inside the TSF. In the case of surface mine, of course, you will still need an additional waste rock pile for the excessive amount of waste rock that will be produced. But I'm not sure I have answered completely your question.
Yeah, I guess just obviously a key focus at the moment to deal with liquefaction issues is buttressing with rockfill on the downstream side of the slopes. So that pre-planning or pre-thought to put the rockfill on the downstream side to begin with deals with the liquefaction issue. But anyway, okay.
Yep.
Just to follow up on that comment, I think one of the things with these waste rock inclusions that you haven't mentioned is that they can actually be quite effective in getting rid of nag waste rock that isn't suitable to be placed on the downstream slope. So I think in some applications, I'm not sure about the exact case at Malarktic that you're showing, but to that point, sometimes if you can't place it on the downstream, they're using it inside to get rid of nag at the same time.
Any other questions from the audience? You have? Okay,
I
go ahead.
have one for Thomas. In case of backfilling the pits with the envelope and creating this permeable layer all around, are there some issues with, like, over time, the fines to fill up the voids in the coarse material, and then how to deal with that?
Yeah, that's a good point too. Yeah, then there might be some mixing also the same that we've observed in the surface tailings storage facilities with inclusions. We've not been there so far, but maybe that would require having a permeable envelope which is wide enough so that even though there is some intrusion of fine particles, it will not decrease the ability of the envelope to conduct water around. Yeah, that's something that maybe then it need to be taken into account in the design, that we are a bit like a factor of safety, yes, in terms of width.
There is a question online. I think it's for you, Thomas. What will the the effect of beach formation by adopting the waste rock intrusions?
Actually, it's positive because this beach will be more permeable, so it will facilitate also the dissipation of the excess water pressure close to the inclusion. So, because yes, there will be a beach anyway. We have observed this at Manartic, even though it was a second tailings, but it was drying faster than the rest of the TSF. So it's positive.
I have a question for you. So you mentioned that in order to avoid the formation of oxides, we kind of should develop the cover in time. So when you talk about active tailings dams, you realize that the saturation kind of keeps dropping. So when do you think that you should actually do it while you design the closure, or do you do it in parts? I don't come from this background, but it's just a curious question. So when you have an active dam, do you kind of recommend that we should start designing the covers in portions where they actually, like you're done with the tailings dams to kind of avoid this oxide formation? Like what would be your recommendation?
Yeah, I guess it's a bigger challenge when the lifetime is becoming longer and the volumes are longer. Yeah, but maybe Thomas has an answer to that. I guess for some other types of consulting projects, we recommend intermediate covers, but that's again adding some weight. So I don't know if there are some other new.
It's a very interesting question, and many people have tried to go with this progressive reclamation. We call that progressive reclamation. It's complicated in terms of operationalization because you don't want to put too much material because you lose space, you lose money, but at the same time you want to avoid acid mine drainage. We're still not there. We're trying, and probably I believe that with filtered tailings it will be easier because we can actually have some traffic on the top of the tailings of the TSF, but it's not in place yet.
I guess it depends on the neutralizing capacity of the tailing. If there is at least a little bit of neutralizing capacity, you can wait a little bit.
Exactly.
Okay. Jerome, last question for you. So would you like to kind of talk about a bit on the cost aspect of kind of designing something from a lab scale till a field scale for a specific case? Like how do you convince the mining industry that they should probably kind of customize a water treatment plan to kind of avoid the damages from the leachate? So would you like to address that?
I could not tell you how much did it cost over 10 years because they were such different funding, and each project, like the first project, were addressing other mine sites, but it was because we have to start again. The team was changing over time. It was especially inefficient, and we took 10 years, but we did it for Rio in France. It can go much faster and much cheaper. Like for Rio, pretty similar water, just more manganese. It took like 4 years, and it was, I think, less of, maybe 250,000 euros, something like this, for the lab scale test and the pilot test.
And one last question. So now we are in a transition to moving towards filtered tailings. So the kind of tailings, does it how does it change the methodology that you have to apply to kind of develop these treatment plants?
There's huge change because on this mine site, water was coming from the incline. And it was not very acidic, not very contaminated. When we are working on tailing dam seepage, it's much more acidic, much more contaminated. And if you want to design passive treatment, you can do it if it's low flow rate or if it's low contaminant. If you have high flow rate and high contaminant, you cannot do it passively anymore. You have to switch to active treatment. So yes, there's big difference. And okay, sometimes maybe it's still low flow rate on a TSF seepage, but it's much more acidic and several grams per liter of contaminant.
Thank you. Yes, Rosa, can we have the microphone, please? Simon, yes. Thanks. There you
It's for Thomas, actually. I just want to know what could be the limitation or the challenges you encountered while using integrated approach of risk assessment than the traditional way.
Can you just repeat one more time the question?
Yeah, what could be the limitation or the challenges that you encountered while using integrated approach of risk assessment than the traditional way, regardless of all this?
That's also one part of the integrated mine waste management is to take into account, yes, this risk analysis and to try. The main challenge I would say is that it's very emerging technologies. So some of them are applied in practice, but some of them are not yet. And we often say in the industry that mining companies don't want to be the first, but the second. So just let someone make the test first, see how it works. So that's the main. Even though it seems to work well, of course, there is still some specific site conditions to take into account and to just see at the large scale, because even though we focus on the applicability and on the upscaling, still unknowns are remaining. So yeah, it's a work in progress, so the risk is still there, yes, of course.
Do we have any other questions from the audience? I think everybody is hungry, so we thank our speakers once again, and we head for lunch, so I think we can enjoy a longer lunch. So we meet in an hour and 10 minutes. So we meet again at 1:30. Yes, thank you.
Welcome back. Welcome back to these last two sessions. And we start with session about industry challenges. I just wait a few more seconds for you to take a seat. And here the next speaker will have the challenge to keep everybody awake after the lunch, not only people here in person, but also people online. So next speaker is Yuuki Silveira Miura from Hydro Norway, legacy manager at Hydro with a decade of experience in aluminium industry, specializing in innovative rehabilitation, closure projects, and ESG practice in tailings management. The floor is yours.
Thank you, Luca. Thank you for the introduction, and thank you for the invitation. It's the first time that I'm speaking on the conference, so take it easy on me, please. As Luca mentioned, I'm legacy manager at Norsk Hydro. I've been working for Hydro since 2015. I started back in Brazil. I'm Brazilian, and recently I moved to Norway to enjoy the winter, Norwegian winter and darkness. And since last year, I'm working on GISTM implementation on our tailings facilities in Germany and Brazil. So when Luca invited me to speak about the industry challenge, toward tailing management and tailing safety, of course, I could not stop thinking about GISTM. GISTM, as you know, it has been extremely challenging for the last 3 years for the ICMM members. And as you will see in these next slides, implementing GISTM means that we are overcoming the main challenge on tailing management system, in tailing management and tailing safety. Oops, it's not here, it's here. So today, I divided the agenda today in 4 main topics. First, I'd like to introduce the current scenario of mining industry, what is happening around the world. Then I would like to introduce what GISTM means. I'm not sure if everyone have heard about it or has any experience about with GISTM. I know that there are lots of ITRB members here, so that's very nice. I'm very keen to hear your experience in being ITRB board. And then also I'd like to present how we work towards the GISTM implementation, to GISTM conformance in Norsk Hydro in our tailings facilities in Brazil. And finally, discuss what we can expect, what's next in terms of GISTM, in terms of tailing management. And again, listen for all your experience. So I hope that at the end, I really hope that first you don't fall asleep, because I have this challenge to keep you, awake during this presentation. But at the end, I hope that you understand what GISTM is and understand what the main topics that it covers. Also identify the challenge and the benefits that GISTM can bring to the industry. And finally, discuss the trends for the next years. Yes, so over the last decades, we saw lots of demand growing for the minerals, and recently, due to clean energy transition, we expect that this demand will keep increasing, right? So we believe that the energy transition, and we have seen it, will lead to more need for mining and more need, of course, for tailing facilities. Also, we've seen lots of, here I put government support, but it should be better to rebrand this as policy support. We have seen many countries introducing new legislation, new policies addressing critical minerals production. So here I brought some examples. First is the European Union released March this year the Raw Material Act. Also, our government in Brazil, from Minas Gerais, we recently launched the Lithium Valley by our governor. So we see lots of engagement, funding, policy engagement of the government around critical minerals. Then, of course, as I said, if you have a higher demand for mining products, we will consequently have a higher need for disposing this, disposing the waste, disposing the tailings. And of course, if you have a more higher volume, more numbers of tailings, you increase the risk, increasing the risk for collapse and catastrophic failure, as we have seen the last year. So we can conclude that critical minerals for energy transition will intensify this need for tailings disposal, and recent dam failures have spotlighted the industry in tailing management. So what is GISTM? Oops, nope. Yeah. So given recent failures that we have seen in Brazil and also in Africa in recent years, ICMM has released in 2020 the new standard, or the global industry standard on tailing management. GISTM is divided in 6 topics, and that encompass 77 requirements to be met. And actually, most of these requirements actually are about environment, social, and governance. So 60% of these 77 requirements are regarding ESG, more than technical issues. That's also very interesting. Also, the GISTM classified the tailings facilities in 5 classifications according to the potential consequence in case of failure. And as you see here in this table, GISTM has 5 classifications, and it will be classified according to the worst case scenario of one of these categories: population at risk, potential loss of life, environment, health, social and cultural, and infrastructure and economy. The GISTM is quite ambitious and sets a high bar in terms of tailing governance, tailing management. Actually, sometimes GISTM is even more restricted than some regulations. And also, GISTM is about all the tailings facility life cycle. So from concept, design, operation, closure, until post-closure. So it doesn't matter if your tailing facility has been closed or it's still in the design phase. GISTM cover all the phases of your tailings facility, of the tailings facilities. Oops. So, what are the main? Let's deep dive a little bit on this each of these topics. Of course, here the idea is to bring the main challenge of each of these topics. But of course, the challenge vary depending on where you are, the location, the country, and the social context, environmental context. But here, the idea is to bring, the challenge that we have faced in Norsk Hydro, in our tailings, mainly in our tailings facilities in Brazil and Germany. So first is affected community. So social performance are spread around all of these 6 topics. Social performance probably are the most, I would say, the challenging, mainly in our case in Brazil, because beyond seeing social performance is just as a community engagement, we also have to see the organizational aspect, the legal aspect, and how to involve them in our daily decisions on tailing management. Then the second one is about an integrated knowledge base. One of the main challenges of these topics is integrating the environmental, social, and local economic context on tailing management. And for us, the most novel and I think the challenging aspect here was bringing the climate change to the tailing management on our tailings facilities, how we can integrate the climate change in the design, the concept of our tailings. Then design, construction, operation, and monitoring. This is more straightforward because this topic was probably the most technical topic. And actually, since this, we have been developing studies and design documents along the years. So this was quite straightforward. Actually, we had most of the documents already in place. And for me, the second most important aspect on GISTM is management and governance. So here, organizing the structure, defining the accountability of accountable executive, engineer of record, ITRB. This was quite challenging, mainly because the definition of the corporate responsibility and business areas responsibility, we had to sit together and define all this accountability and responsibility throughout all the organization. So that was quite challenging. Finally, besides just the emergency response plan, GISTM asked for a recovery plan after a catastrophic failure. And that was also new for us because, of course, we already had the emergency response plan in place already, but the recovery plan was, I would say, a more innovative, a more new concept that has been brought by GISTM, and then we had to develop from the scratch. And finally, public disclosure and access to information. This, again, was quite new concept. Of course, we have our annual report where we disclose lots of information there, but a disclosure specific for tailing management and for our tailings facility, that was very new. So we have established our website, a new link in our website where we disclosed the Principle 15, which requires a kind of a summary of all the 77 requirements that we have been established in our in our tailings. So anyone that wants to have more access, we also have a communication channel where you can, send an email to us requesting information or for more documentation regarding our tailings. So how we got in conformance to GISTM in Norsk Hydro. I'd like to introduce our tailings facilities. So here I can divide our tailings facilities in two categories. And NGI's fellows, they are tired to see these pictures, I think. Mainly Luca and Farrokh, they have been working on it for almost 2 years now, but I have to repeat again. So we have, so I divide in two categories. The first category is the active tailings facility. So all our tailings facilities in Brazil, they are in operation. They are active sites. However, in Germany, we have how we call it as a legacy site, but but we can also call them as inactive sites because they are not under operation anymore. So here in this picture, you see DRS1 and DRS2 in Brazil. Both are under operation, and this is our tailings facilities, 1, 2, and 3, and Schwandorf. So in Brazil, we have 4 tailings facilities. Their classification vary in very high to high, and all the classifications in our German sites are below very high classification. Therefore, the deadline for GISTM conformance in August 25. Here, it's interesting to note that, when you compare active and inactive sites, there are pros and cons. The challenge and the opportunities, I would say. The challenge about legacy site is that there is no one there. There is no one that we can rely on to request documents, environmental, social department that could support us in GISTM implementation. On the other hand, on the operational side, you have the whole organizational structure, all the teams that could support in developing all the requirements. On the other hand, the legacy sites, these guys here has been sitting there for decades. So it's have been integrated with the local landscape for years, which is good because you have a more stable facilities, which means also less public concerns. But when it comes to operational side, you have a higher public concerns because it's a daily operation, right? Okay. So here, the intention here is to inform how we delivered step by step the main, not the main requirements, but the main activities around the GISTM implementation. So, of course, lots of these works also happen in parallel. It doesn't mean that we follow exactly these steps, but it's a good way to kind of follow and understand how we implemented it. So first of all, despite we already had an organizational structure in place, here it was important to define the responsibility mentioned in GISTM, accountable executive, VOR, and find a good people, good group, high-skilled group for ITRB. This was quite also challenging. Design document was straightforward, as I said, so over the years, we had all of this documentation in place. However, for the legacy side has been quite challenging because first, the language barrier. Most of the documents there are in German. Second, there is no document in digital form. Most are physical, and we have to, scan it, translate it, and, get the information, and compared to modern tailings facilities, we have from that time, we have much less information compared to current tailings facilities, right? So after you have designed your documents, after you have a good organizational structure, it's time to understand your socio-economic context and environmental context. This is extremely important. In Brazil, we had, the community engagement has been done by our social team for years, so that was not, the social context is well understood. However, again, this can be very challenging for legacy inactive sites because this interaction with communities have been lost or at least have been reduced because the fact that there is no operation there. In terms of environment and climate assessment, this is again, we have been carried out lots of environmental studies in Brazil. We also have been carried out environmental studies in Germany, but here the climate change assessment was our focus point. So we had to redefine our models, redefine the max precipitation by return period, and integrate this information with our tailings facilities. Here, I will not dare to explain to you, risk assessment, ALARP, flooding, because you are the experts here, but I can mention that the definition of ALARP, as low as reasonably practicable, it's extremely, can be very complex and can be very challenging as well. Then, after you have the definition of your flooding areas, your risks, your ALARP, it's time to run the drills for your emergency response plan, engaging the communities, and here again, it can be challenging for both sides. First, you have a limited public system in Brazil, so a limited public resources that sometimes can make the things more complex, more complicated. Also, the communities, our neighborhoods are not very, I would say, used to have drills, used to have simulation, emergency simulation. So engaging the community here, showing them the importance, also in a manner that you will not raise too much concern, is quite challenging. Third-party tailing safety program was our routine already, has been our routine in Brazil for decades. So this was, again, not a challenge at all. And finally, the publication in our website and our material about all of the summary of all of this. Finally, by August 5, we got in conformance with GISTM for our tailings facilities in Brazil. Oops. Yeah, so after August 5, we ran a kind of assessment on the disclosure of our peers to understand what they have been published, what were their challenges, And as I mentioned before, GIS-TM implementation is extremely challenging, and some companies are still working on it. This assessment demonstrates that actually less than 50% of the ICM members claim full conformance, but they are, most of them, they are most of us actually, we are ICM members, will commit to become compliant by 24, 25. What was interesting to note that lots of members already had performed the third-party validation in their self-assessment, and the level of disclosed information was varied among the peers. So now we're going to have the next ICMM meetings in, with daily management group in November to define a better alignment and the lesson and learnings from the GIS-TM after we have published in our website. So it's going to be really interesting to get together with the peers and learn more about GIS-TM. So what has changed since 3 years ago? So here I brought some feedbacks of ICMM members. I understood that these 5 topics were the main improvements brought by GIS-TM. So although some members have partially implemented GIS-TM, the improvements brought by GIS-TM is very clear, is very evident. So first, the governance, as I said before, the definition of accountability, the definition of organizational structure was very extremely essential. The transparency, so now we have a more transparent communication channel with the stakeholders, which is also regarding to reportability. So now we have a well-defined way to report, to show our information to the communities, to the stakeholder, which is required by GIS-TM. We could see that GIS-TM also helped us, support us to engage more and more with our neighbors. And finally, a multidisciplinary team. So the standard call for, these relevant issues regarding ESG. So this pushed us to have a more multidisciplinary team together working on tailing management. So we have now a much better integration with environment, social, finance, a governance team when we speak about tailing management. And what we can expect next? What's next in terms of tailing management and GIS-TM? So as I said, third-party audit has been done by some members, but we believe that this will become more common, and probably GTMI will come up with, I don't know, maybe entity that will validate this third party or create a sort of a certification for GIS-TM conformance. Safe closure, this is a topic that we are working on now, and we believe that most of the members will work on the concept of safe closure, because according to ICMM conformance, as long as you can argue that and the claim that your tailings facilities are on the safe closure, there is no need to follow up the GIS-TM requirements. So maturing this concept of safe closure probably will be one of the main activities between the members. Legacy sites. So the question here is, does the legacy sites require exactly the same approach to active site, or should we adjust the GIS-TM to fit for purpose? That's one of the questions that still remain. And more integration with engagement with project-affected people will keep one of the main topics to be discussed. Yes, so that was my presentation. It's always hard to conclude a presentation, but I will be very happy to listen your experience and your thoughts about what we have discussed so far. Thank you.
Thank you very much, Yuuki. I think it was important and evident from your presentation that to go towards safer tailings dams is not so only a matter of technical aspects, but also social aspects to take into account. For the questions, we do as we are doing, so we go forward with the next presentation and then we take all the questions. So next presentation is made by Dr. Kai Inge Holthe-Seim, which is a production manager at Titania, Norway, with a background in mineral processing and extensive experience managing crucial mining facilities. And then I think it's also the presentation will be shared with Dr. Hilde Marie Schellesvig, that has a PhD from the Norwegian University of Science and Technology, NTNU in Trondheim, with 20 years of experience working on projects concerning dam safety, including dam reassessment, dam break analysis, spillway design, and tailings dams. Please go ahead.
Thank you for the introduction and for inviting us to this workshop today. We will go into a project for our tailing facility and what we have been working with. But now we will start to tell a little bit about the company to start with. There. So the company was founded in the beginning of the 1900s. And when it was founded, it was aimed for looking at the ilmenite deposits in the area. They know that it's very known for its deposits, and they didn't know what they could use it to at the start. So they started to focus on research, on how to use the titan dioxide content in the ilmenite. At the same time, there was a parallel process in the States. But in 1916, they were able to find a solution for this, and they also established Kronos Titan in Fredrikstad, which was a sister company. And the first delivery of ilmenite was done at that time. So the pigment production is then replacing the lead used in paint. In the beginning, there was an underground mine in Sandbekk. And in the 50s, they needed to decide if they would go further down to the next level or search for a new deposit. So based on the new techniques for searching for new ore bodies, they decided to see if there were any bigger deposits in the area. And that led to the discovery of Telnes deposit. So from 1954 to 1960, all the infrastructure, equipment, mining equipment, buildings was established, and the production started up in that area. So from 60 to 65, we were operating at Sandbekk and at Telnes. At that time, it was among the world's largest deposits, and as then and today, it's still a cornerstone company in Sokndal municipality. Titania is an American-owned company, and we have been owned by Americans since 1926. So they've been a very solid owner since then. Titania is placed south of Stavanger, and then we have the Kronos Titan in Fredrikstad. And they also have factory in Nordenham, Leverkusen, and Langenbrugge in Belgium. The headquarters are in Dallas, And we also have factories in Varennes and in Lake Charles. Kronos is the third largest producer of pigment worldwide. Back to Sokndal, you can see the mine in this area. It's an open pit, and the landfill is placed here. And we have the ore dressing plant close to the mine, and the end of the ore dressing plant is here at Jøssingfjord, where we also have the shipping facilities. So there's about 200 shipments every year going from Jøssingfjord out to Europe and the Asian market. Before we moved the deposition to land, we had a sea disposal in Jøssingfjord and here at Dyngerdypet. This is just showing a cross-section of our operation. It's 4.5 kilometers from the coastline. We have a drainage tunnel at the mine, so today we are pumping water to the drainage tunnel, and by gravity it flows out to the sea. The ore is crushed at the mine and placed in mountain silos in front of the ore dressing plant, where it's treated further for separation. We also have a tunnel between the Humedal here and Jøssingfjord, where we call the drying plant. And we are pumping back tailings from this area and out to the disposal area. We have also 2 mountain silos at the fjord, where we store our products. The open pit. It was opened in the 60s, and today we are, the lowest level is 5 meters above sea level. The highest point are 305. We have a mine plan to 2070, and that we will be 40 meters below the sea level. The length is 2.7 kilometers, and the deposit will continue to the depth after the end of the open pit. But how they will proceed then will be depending on the market situations. The total, this is just to show the total rock capture. So the waste rock is an autosite and stands for 70% of all the volume that we are moving. Tailings represent 20%, and 10% is then back to concentrate and sent to our customers. So we need a place to do our operation. The storage, the tailing storage facilities. So we have, this is a picture showing how it was before we started the project. You have the ore dressing plant here, open pit, dam 5, and dam number 6, and dam 1 here, and pond here at the western part of the tails area. So we are pumping from the ore dressing plant, and the pipes are going out to dam 5 and 6, and also we follow the infrastructure down to dam 1. Today we have a production represent 2 million tons of sand. And we were in interval of raising the dam 6 meters every third year. We have a license to build up to level 300.
So the project that I will give a brief overview of is one, perhaps the most interesting and challenging project that I have worked with. Sweco has been the consultants of the project, and my role in this project has been to be the project manager of all Sweco's work. The consultant work that we have done have included everything from environmental issues, road engineering, instrumentation, hydraulic engineer, and dam safety, which is my specialty. And then, of course, tailing dams, and a lot of other activities. We have used colleagues from a lot of different offices at Sweco here in Norway. But I have to mention that for the tailing dams, it has been crucial to be able to use the expert that we have in tailing dam in our Sweco offices in Sweden. And the main expert has been Magnus Ljunggren, that's located up there. So if not, they have been available to help us. I'm not sure that the project has been such a success as it has been. The presentation here will be more of an overview of the project, and I don't have the details of every aspect of the project, of course, since it's been a large project. So I can already say now that I could not answer all questions if you have detailed technical questions. But I'm sure that when the project has landed and all reports have been delivered, there will be most probably quite many articles that will be written and a presentation given by the experts that will concerning the technical details and the findings of the tests that have been done. And also Magnus will be here today, this evening and tomorrow, so if you have questions, it's possible to ask him after or later today and tomorrow. So then I will go to the dam. The main dam, Gruve Dam 1, is this dam here. And the picture here is from 2021, 2 years ago. So this was how the dam looked before the project started. If we look how the cross-section looks, the main dam 1 was planned and designed at the end of 1980s, beginning of 1990s, and was designed by leading international experts on tailing dams and Norwegian experts on geotechnical issues. So then, of course, several designs was discussed, but as many other dams designed in that area, it was decided to use a dam, of a starter dam, and an upstream raise of the dam. The starter dam at the Titania is about 46 meters high, and then it was raised, planned to be raised by 6 meters raises up to the final height of 100 meters. It was also planned that it should be possible to extend, to heighten the dam up to 125 meters if that was something that Titania wanted in the future. So then in 2020, there was a plan for the raise of the dam from 82 meters to 88 meters. At the same time, we all know that there has been several dam failures of tailing dams. So based on that, and also based on results that from some of the pore pressures that was installed at the dam, some results in shorter period was not easy to explain. So combining these two knowledge and perhaps some more, it was decided that, or it was recommended from Sweco that there should be done some geotechnical tests of the tailings. So test was carried out during the spring and summer in 2020, and analysis was carried out during the autumn. And the test told us that the tailings had layers and that some of them were loose and partly saturated. The pore pressure also in some areas were higher than registered in the existing piezometers. And the material in some layers also had the potential to liquefy. So based on this, dam break analysis was carried out for the dam. As you can see, here is the dam. And if you have a dam bridge, the floodway will go down here and to this area here where you have a small village. And then continue out in the fjord and out to the sea. So the finding from the dam analysis was that the downstream village called Onasira will be highly affected if a breach would occur. And based on that knowledge, the dam was reclassified from the lowest consequence class in Norway to the highest consequence class. So the reclassification of the dam, of course, led to a whole new set of regulation that had to be fulfilled. The dam was then re-evaluated by Sweco in 2021, and the conclusion was that the dam did not fulfill the dam safety requirements according to the Norwegian dam safety regulation, as well as international recommendations. So it was recommended by Sweco that the strengthening measures should be taken. At the same time, a safety zone behind Dam 1 was established, where in this area no more depositions should be carried out before the dam was strengthening. The reason, of course, was that it should not be added more load to this area. And in order to keep the production of titanium going, several internal cells were established in the area outside of the safety zone. And also other work were initiated. Among them were to minimize the water flow into this area and to reduce the level of the pond and also to reduce vibration from blasting in a pit so that the load on the dam should be minimized. And also programs on monitoring and instrumentation was enlarged. And the emergency and evacuation plans were updated. And public, of course, was informed. So this is the cell that was constructed in order to keep the titania production going. Several cells were placed in the part of the TSF that was far from Dam 1. The smaller cell was smaller cells up here was established first, and when this wasn't used, more cells was established, and then cells were established here, and the tailings were started to be pumped out in this area, while a larger cell was constructed in this area. And I think perhaps you will say a little bit more about how we operate it.
Yes. So this was a change for how we were working traditionally in the TSF, and the construction of the cells started and was not finished before we started to operate in the area. So cell number 1, you see in the backhand here, when this was finished, we started to deposit within this, and the construction continued downwards in this system. There were several contractors involved, and the challenge here was also to have very good communication internally, so we know the framework that we were working along, so there was no misunderstanding of what we were going to do and what the restrictions were during operation. One of the big challenge here was that to handle the water, the process water, due to particle transportation. So we would like to have as high water level as possible to gain as much sedimentation of particles as possible before we pump the water further on. So we needed to find a balance where we could reach the maximum of sedimentation and transport of water to the pond. So then we have, here you see the pump installation for cell number 2. It was pumped to a container here, and by gravity it flowed over the whole area through the pond. Preparing the dam 5 area, you see that we needed to establish infrastructure for the equipment to do the ground investigations. It was quite soft. So the data that they needed for establish the new cells for this area was based on that. And here you see the cells established and ready for use. So during the operation, we were able to optimize the water levels within the cells, and we deposited also from the cell wall. So the pond for this area would be more in the middle and not against the different cell walls.
So as part of what was carried on when this knowledge about the Dam 1 was found out, of course, to enlarge the instrumentation plan was one of the main objects. To get continuous monitoring of different instrumentation. So the water level in the pond was of course measured. There was installed a lot more piezometers in the Dam 1 area, just upstream of the dam. So precipitation is monitored, leakage downstream of the dam, the turbidity, and of course then vibrations caused by both the blasting in the open pit and also due to construction work was monitored, and then deformation. I have a special slide about the deformation because that was looked upon as quite important to have a good measurement on the deformation. It was seen as crucial because, as we all know, then when we have loads on the tailings, you will get deformation, and this could induce excess pore pressure, causing reduction of the stability of the dam. So it was very important to have a good overview of the deformation that occurred in the dam. And just to tell a little bit beforehand of what happened was that this deformation was monitored during the whole construction, and it was compared with the deformation that was found by finite element analysis. To conclude, it was found no unexpected behavior during the whole construction period concerning deformation. To measure the deformation, there was used a ground radar for the lower part of the starter dam, and there was deformation bolts. That was the old deformation measurement that was originally. And then there was installed totally 60 points by prisms that was continuously measured by a total station. So they had the measurements once every hour for each of these 60 points. So parallel with this, all this work here, there was worked with a master plan for how to strengthen the dam. This master plan was finalized in 2022, in the beginning of 2022, and it described the design principle for how to fulfill the dam safety regulations. The stabilization measures that was recommended was to construct a rock fill buttress against the downstream face of the existing dams in order to increase the embankment stability. The construction was recommended to be divided in three phases to speed up the rehabilitation work. The idea was then to construct one phase parallel as the design of the next phase was carried out. The first phase, phase 0, was preparatory work and access road to the dam toe. And then the construction of the downstream buttress up to the top level of the starter dam was the phase 1. And phase 2 was the construction of the buttress from the top level of the starter dam up to 88-meter high dam that included the raise of 6-meter height. So phase 2 is the phase where the main objective occur, where you stabilize the upper part of the dam that has very need of strengthening. And then it was also, of course, important for Titania to have a design that could allow the dam to be further raised, either by a centerline or downstream raise. So one of the first challenges that we come up with was how to transport the rock fill from the open pit here down to the dam toe. As you can see, the landscape here is not very easy to construct a road in. And the alternative, if you should use a public route, you have to go all the way around here. And it doesn't just get to and fro, it's go up and down also, so it's a terrible road. It's not possible option. So there has to be a way to transport in this area here, down here, or here. So the solution was to, in fact, build a dam in this area around here. And this picture here is from the preparatory construction work, where the area downstream of the dam the soil was removed and the vegetation And the road will come up here. And I have a lot of pictures from the project. Here is the road. As you can see, it's quite steep, and we need a lot of blasting for making this road. And of course, when you have this measure or giving this restriction of how much vibration you can accept on the dam, it is a challenge to make such a road as this. But the vibration measurements was taken 3 places on the dam and on the rock close to the dam, so they had to be very careful when they were doing the blasting. This is also from the road construction. And here is the final road that comes from up from the deposition area, going down and to the dam tower. Here is also a picture from the first part where you have, or for the phase 1, when you are building from the dam tow to the starter dam. And this picture here is quite funny, but if you see the date, it's about 1 year ago. Then we were in this area here. The start dam, top of the start dam is here, so we are about halfway up to the top start dam. The construction carried on. Also, of course, it was a discussion for how long the material should come from this area before it was possible to bring the material from the upper end and down instead. Yeah. This is just a model of how the road is located up here, and you fill up rock fill in the area. And then soon we started with the phase 2. Then it was possible to bring rock fill from up from the dam crest and down. Of course, that was a kind of a milestone when that could be done instead of driving the long way down to the dam tow and up. So this is phase 2 when we are, it's phase 2 or phase 1B, just between phase 1 and phase 2. And this is where we placed the starter dam to the new dam crest. And it also had to be mentioned that we were doing several field tests that were carried out to identify safe construction. And one example of this was testing of consolidation properties of the tailing to find the time before full dissipation of the excess pore pressure, because this information was used to set the rest time between subsequently lift of the rock fill, because you don't want to have this pore pressure that's in the area that could cause liquefaction of the tailings. So as you can see, in Norway we have different weather conditions. It was not all day that was clear blue sky and good weather and good warm weather. So also look like this some part of the year. And then finally now in June, the dam was strengthened and raised up to 288. So I have, or Magnus have made a time lapse of the construction. You will see that there are varying lightning conditions on the dam, and also some pictures of with snow and some without snow. So we will It's not perfect, but it's how it is in Norway, perhaps. So I will show this. This is the first one we prepare the foundation. And then you will soon see the road comes in this area here. And then we start to fill out in the dam toe. And the rock felder is then placed up in phase 1, up to the top of the start dam that is here. So this is about 1 year ago, and now we come in the late autumn. And then we are more or less into the winter. You see there's snow some days. Then we soon are on the top of the old dam and start to raise the dam again 6 more meters. Until it's finalized now in June. Yes, I think you will say a little bit more about plans, or what we have, sum it up, what we have done.
Yeah, so this is a short list for summary, but we've been through a lot of different work in different aspects of the area. The map is showing the impact of rainfall into the TSF, and we needed also to establish flood handling system, and this map is also valid today. So there was a lot of work to try to minimize the impact of water. So the yellow part there, we made ditches, and based on gravity, we were able to lead the water away from the area, and we also had some smaller area on top of this mountain and on the west and east part of the dam. So that in total we reduced the impact by 17%. So we have one flood handling for this area, one flood area handling system for this area, and one for all of this. And this will be in place until we have the next level of flood handling established. We also have updated the emergency response plans, and we also have the emergency aggregates to supply the water treatment system for this area. Based on the work and the reclassification, we also have now established a deposition plan, which is showing how to deposit behind dam 1 in this area, which we follow, and how the pond could be raised in this period. The deposition plans will also show the next level of rise for dam 1, and when we are also moving into new establishment of dam in these areas. Through last year, we also had to recruit and look at the organization to be able to handle the situation we were in. We had to recruit engineers for project management, and the class for Dam 1 also requires a competence for the dam safety engineer, who is going to be the responsible person for Dam 1. We used a lot of time to try to find a candidate. We had a dialogue with NVE also to be sure that we were looking for the right type of competence that they required. And finally, we succeeded at the end finding a right candidate for this job. And that's Iselin Mydland. She is also sitting here today, and she is now undergoing training for taking over this responsibility. During the project, we have been working with NVE, with NGI, Sweco. There have been different experts involved, and been an open dialogue and a good communication between the different experts and aspects of the project, which I think also been part of the successful development of the work that's been done. So, looking ahead, there's a requirement for the flood handling system that we need to adapt to the TSF area. We will work further with the deposition plants. We see this as very good tools to predict when to rise and how the area will develop based on how we deposit. We need to establish more dams, and the instrumentation plan is also going to be updated, as well as the emergency action plans for this area. And I will also show the drone for how they're looking, how the TSF is today. So as you see Dam 1. See the infrastructure that was constructed for the project. Now we move back to Dam 1, and you see how the water is now going to the pond. Okay, thank you for your attention.
Well, thank you very much for this, for sharing with us this very interesting case study. Thank you very much. I think that we have enough material for questions, for taking questions for these two presentations. Yuuki, if you can come, you can join me here. Do we have questions here? Curiosity or questions? Yeah, Farrokh is over there. If you can, Yuuki, if you can move a bit on the right, because otherwise you will not be seen. Yeah, great. Yeah, thanks. Yes, Farrokh, please. Yes.
My question is to Yuuki about GISTM standard. It's called a standard, but as far as I understand, this is kind of something that's the industry voluntarily is following. And maybe guidelines would be more appropriate, but I'm just wondering, has any country adopted this as kind of a compulsory standard that should be followed by the industry? Or still it's on kind of voluntary basis, depending on the company who wants to follow it or not?
Yeah, so far as I know, it still is voluntary based, and of course there are some overlaps if you compare to some regulations. For example, if you see Brazilian regulation that recently was improved a lot in recent years, there are some similar requirements when you compare regulation and GISTM. However, I haven't heard about any nation, any country, like taking GISTM and modifying its regulation from GISTM. What I also, studying GISTM and implementing it, we could see that lots of requirements and concepts from GISTM actually was taken from Canadian. It's a Canadian tailings regulator. It's a standard from Canadian government, which is probably one of the most complete and well-designed tailing regulation around the world. That's what we could identify. Yeah. CDA. Yes, CDA. Thank you.
Yes, Annika.
Just to comment on the same, on your question, as far as I know, it's the standard is developed by ICMM and some other organizations, and all the mining companies that are members of ICMM doesn't really volunteer to follow, but has to follow as an ICMM member. But then other companies can also follow and say that they follow the standard. Or
yes.
And I know there is also some companies that sort of state that they don't follow the standard, but follow other standards and believe that's enough.
Yeah.
And then in Sweden, for example, the dam safety guidelines for tailings dams are being revised, and the standard is considered in that work, but it's not like the standard is 100% implemented. So voluntarily, except for the ICMM members.
Yeah, exactly. So we, the members sign this commitment to be in conformance by the deadlines that, as we saw, it's not very straightforward, but all the members are working continuously to get in conformance as soon as possible. And yeah, about this Swedish regulation, I didn't know about it. Interesting to see that some countries have taken GISTM as an example.
It's not regulation, but they're going to consider it within the guidelines,
okay.
Which is just a guideline and not a regulation.
Interesting. Other questions from the audience? I know there are some questions from what are the other possible solutions discussed other than rock buttress for strengthening the dam? I guess it's for you guys. If you have discussed other options.
I think we discussed a lot of different options to reduce the loads, and that part of it's not strengthening, but action that was taken before the strengthening. But I think the strengthening was the obvious solution to this buttress, downstream buttress fill was the only solution that we found adequate for this dam. Yes.
Was consolidation a solution, trying to kind of having some wells and to have consolidation, or not?
It was discussed, but then I think you have to ask Magnus about how. But it was discussed, yes.
There is another question. Kai and Hilde, can you tell us the angle? I guess it's the slope of the downstream wall of dam 1. What was the slope?
The slope of the starter dam is 1 to 1.5, and from the upper part it's 1 to 2.8. Okay.
Are there other questions?
I do actually. When you mentioned 288, it's from the toe or from the sea level?
288 is from the sea level. Okay. But the top, it's 88 because the center line of the starter dam is on 200. So it's quite easy to calculate. So the top of the dam is now 288. So the height of the dam is 88. So it's easy to calculate. Yeah.
I had a question. So you said that it's one of the rare things that you experience such kind of freezing environment. So did you check into the freezing and thawing of the tailings material? Does it affect? Did you kind of look into that?
Magnus, then I think you have to answer that. Yeah.
And I have my last, I don't know if there are other questions, otherwise I have a curiosity myself. Yeah, Suzanne, please. Again.
Thank you. My question is about the GISTM. And at the very end of your presentation, you mentioned that for legacy site, maybe there should be adapted GISTM. And legacy site, they might be at high risk, both the high probability of failure based on past events. So in what way do you think that the GISTM will be adjusted?
Yes, so that's a good question. Actually, when I said adjust GISTM, it doesn't mean to create the new requirements or adapt sort of in a way to fit for the legacy sites. But, however, there are some concepts in GISTM that it's quite hard to keep the same understanding when you compare active sites with inactive sites. One example is community engagement or meaningful engagement. This word has shown in GISTM everywhere. What meaningful engagement means. When you compare active sites, you have like actively this cooperation, this communication with the communities are it's part of our routine. However, when you compare inactive sites, this is not a routine. This engagement with community, for example, should be different, should be appropriate to inactive, more sort of maybe involving more the authorities than involving the community directly. So when I say that GISTM requirement might be adjusted, it means that some concepts that it's in the requirements should be maybe have different understanding or have different approach to some requirements. But you are totally right, because it doesn't matter if you are legacy sites or active sites. If you are in a high consequence, it's high. It doesn't matter if it's active or inactive. However, sometimes how you face some concepts maybe should be a little bit different. you could not, for example, say that an approach with the communities by website or by different type of engagement is not enough compared to active sites, because active sites, we go to the communities, we do meetings in that place, locally, we engage them throughout the authorities, which it's a meaningful engagement. But this meaningful engagement doesn't mean that it should be the same way for these legacy sites. I'm giving just one example of community engagement because that's one of the, I think, the most easiest concept to bring as an example, you know. So that's my point. Thank you.
Okay, so if we don't have other questions, then we can thank the speakers and we can move. And we can move with, of course, last but not least, presentation. And the session is Standards and Guidelines, and it's Dr. Annika Bielkevic from ICOLD Technical Committee L, Vice Chair of this committee, and she's consultant at Tailings Consultants Scandinavia, Sweden, and ICOLD Technical Committee, as I said, L, Vice Chair, and specializing in long-term stability of tailings dams and aligning them with the global industry standards on tailings management.
Thank you. I think this conference has been very good so far, a success, and I hope my final talk is not going to change that. So I'm going to talk about ICOLD and the Tailings Committee, and many of you might know exactly what ICOLD is, and maybe are maybe part and active in ICOLD as well. But I'll briefly go through what it is. It's a international non-governmental organization to share professional knowledge and information and experience within the dam community. It was established in 1928. And today there is 106 countries that are members of ICOLD. And this includes approximately about 10,000 individual persons engaged in the work within ICOLD. It's an independent professional body. And it was founded for dam design for water dams, a lot of hydropower dams, and for high dams, as high dams poses the biggest risk. And a high dam is defined as higher than 15 meters of the dam height, or store more than 3 million cubic meters of water. And the mission of ICOLD is to lead the profession in setting standards and guidelines to ensure that dams are built and operated safely, efficiently, economically, and are environmentally sustainable and socially equitable. And ICOLD is assisting nations to prepare to meet the challenges of the 21st century in the development and management of the world's water and hydropower resources. So the ICOLD organization is based on different technical committees. Currently, there is 37 committees. Not all of them are technical. But Committee L on tailings dams and waste lagoons is one of the committees that has been for a long time. Normally, the committees set terms of reference for 3 years, and they carry out that work for 3 years, and then the committee is sort of cancelled if there is not more work to do. But all the other committees basically are related to water dams. So tailings has been a small part of ICOLD. But the committee has been growing as the interest in tailings dams and tailings is growing, and unfortunately, mainly due to the failures that have happened. The structure of ICOLD is that the members of ICOLD are allowed to choose a person to represent the country in each committee. The last years we've sort of opened up the tailings committee for more people. So we are 24 countries that are members of the or have representation in the tailings committee. We have 31 members though, so it's a bit strange, I realize now. It should be 24 members, but we have a few more members, and we've started to include or asked all the countries to have one member and one young professional member. YPF stands for Young Professionals Forum, which was established about 10 years ago, and or maybe 15 years ago, and that includes people below 40 years of age. So we actually would like to see 2 people representing each country, one young professional and one ordinary member. And then we have 8 co-opted members and the corresponding members, and we open up for anyone who's interested. Øyvind is managing the list of people, or the email list. So we have one physical meeting yearly within the when ICOLD has a yearly meeting, and in between we have approximately 6 Teams meetings where the committee is continuing to plan and do the work. And the organization today is Andy Small from Klippenberger in Canada, who's the chairman, and I'm the vice chair. And then we have working groups within our technical committee on different topics. We will, from next year, extend the organization a bit with an administrative person as well, which Øyvind has volunteered to take that role for next year. And we recently updated our own terms of reference for the committee. So the main purpose or the main work that these different committees are doing is writing bulletins that sort of serves as international guidelines. So that's sort of the main task that we have. It's sometimes a little bit frustrating. All the work within ICOLD is made or done on a voluntarily basis, and everything should be translated into French. As France was sort of the they took the initiative to start ICOLD, and the central office is in Paris. And the process, the administration within ICOLD is a little bit slow, which ICOLD is working on to improve. And then review and revise old bulletins and update those as necessary. We have for many years worked on a tailings dam register. There is a dam register within ICOLD, which only consider dams according to the ICOLD definition of high dams. For the registry of tailings storage facilities, we include all tailings facilities. We have no restrictions on dam heights. I'll say a little bit more about that later. We will also focus a lot about sharing the knowledge that we have in the bulletins, because just writing the bulletins doesn't really help the industry if people are not using the knowledge. And support the development of engineers, including the young professionals. And we also want to work with other organizations. ICOLD is just one. We have Ramon from ICM, not ICMM, but IGS. No. Yeah. It's a. I've got it on another slide. The last 2 years we've been doing a lot of work with the European Commission, UNECE, who also do a lot of work on tailings, which we didn't know at all. We've been in contact with the World Bank. They changed the staff, and we lost that communication for a bit now. And also interact with all the other ICOL committees that do work related to tailings dams. So with the Committee L on tailings dam, we do everything that's related to tailings dams, whereas for the water dams, there is one on dam safety, one on instrumentation or surveillance, and one on seismic design and so on. So it's divided into a lot more different technical subtopics. So from when the Tailings Committee started, a number of bulletins has been produced. The last one, Tailings Dam Safety, is published as a preprint. And I'll tell you a little bit more about the coming work there. And in the ICOL meeting in 2019, there was a symposium held about the global industry standard. And this is a slide from Michael Davids at Tech that he presented at that time. So this is sort of the group that developed the standard. And then the intention was, as he presented it then, was that the standard will be specific commitments that the mine owners need to fulfill. And below that, there will be supporting guidance from ICMM, Mining Association of Canada, on governance, the governance side of it. And we see that what we can do within ICOL is to support this work on the technical level. So we like to see our ICOL bulletins to be a document to underpin the work of these other organizations. And this preprint of the Tailings Dam Safety Bulletin, it's only available to members of ICOL at the moment there. If anybody is interested, I can provide it, because we want to spread the knowledge that's within there, and the names of the people in the committee. And the outline of the bulletin I like to kind of look at it as a three-legged stool, where the seat could sort of symbolize the governance, and the three legs, the sign, construction, and operation. And then the material of the stool could sort of symbolize the corporate culture. And you need all of these to have a stable tailings dam. You can't just sort of pick one of them. And the Tailings Dam Safety Bulletin is mainly focusing on the design part, on the technical part. But the others are equally important. And this is sort of the table of contents of the bulletin. And at the ICOL meeting in Marseille, last year, we had a technical workshop where the bulletin was presented, which is recorded on YouTube. So if you want to find out what it's about without reading it, you could start there. And we believe that this bulletin is covering most of the important aspects of tailings dam safety. It has a technical focus to underpin the other industry initiatives. And it's focusing on stability assessment and the stability of the facility. And we see this a little bit as our contribution to prevent other failures of tailings facilities. And it's not meant to sort of replace national regulations, but to be a supplement to those regulations that you already have. And the bulletin is yet only a preprint, but we're already planning the work of updating the bulletin. So there will be an opportunity for anybody who has any ideas or comments to take part in that work. So from now on until the next meeting in Delhi in India in October next year, we will work on update this bulletin and put in some more work into especially brittle soil behavior. There will be some clarification and modifications and especially also to suggestions from others outside the committee. The Tailings Dam Registry, we started to cooperate with Church of England and the UNEP because we realized that the ICOL Tailings Committee don't have the financial resources to keep a tailings dam register up to date. Nayan Rana, who was mentioned yesterday in the Cambridge research project, I think he's gathered over 20,000 facilities in the database at the moment. That was part of his research. So it's nobody else has sort of collected so many facilities, and we hope that discussions are now ongoing to see if the Greta Arendal could be the platform for this register. But at the moment, we're not doing so much work until we find out who can host this database. Then it started off as the need of an update of Bulletin 104 on tailings dam monitoring, but we think it's going to be a new bulletin now on tailings dam safety surveillance, which will be a guidance focusing on the link between surveillance and risks, and the trigger action and response plans, and an overview on new technologies. We will also continue to focus on training. With the UNECE, we participated in some workshops in East Asia, and that work will continue, and then we will also focus on Africa and Europe. And the cooperations that we will pay attention to this coming year is the ICOL technical committees on dam safety. They will start the work of writing a bulletin on risk assessment. And the Committee on Public Safety around dams will write a bulletin on emergency preparedness. And the dam surveillance, the Technical Committee on Dam Surveillance have expressed interest to take part in our work on the new bulletin on surveillance. And then ICOL has regional clubs where no tailings people has really been involved before, so we're going to see if we can get some people engaged in those forums as well. And UNECE, ICMM, and ISS, MGE, now I got it right. And then we're planning for the ICOL meeting in India to as we did in Gothenburg in June this year, we had a tailings program every day of the conference, and it was very well received, and we want to make sure that we have tailings workshops and short courses in India as well. So that's what we're planning for now. And this is the ways to sort of see what we're doing through our the ICOL website, have a bit of a general information, and then we have for the LinkedIn and YouTube for the Tailings Committee, where we post information, and we try to record all the workshops and things we participate in to make it available for anyone who's interested. So thank you.
Thank you very much, Annika. And I just ask if there are any questions among people attending, please. I can start with one question, curiosity about the dam registry. I know the Greta Arendal database together with the Church of England and all these kind of things. I found it very interesting. But of course, not all of the companies are applying with data. And the other thing is that maybe it can be that there are tailings dams, legacy dams, or like dams that are owned by nobody at the moment.
Yeah.
Those ones are kind of perhaps the most challenging ones.
Yeah.
How can we map them?
There's Nayan Rana. He was looking into using AI and satellites to find tailings dams, but the legacy sites are kind of difficult because they can look like anything. Water dams, I think work is being done this way because you have the water surface and you can look at the terrain around. But the mining sites and tailings facilities looks very different. It's very difficult to train the AI. But I think Nayan Rana is involved in a project to start to train an AI with the sites that we have. Nice. So that's one way to sort of find out when you can't get the data from a person. But then, as he's been working on this for quite some time, I know he's been approached by universities in China who want to give him information. So he's sort of become the registry guy, and and information is starting to flow into his register.
That's good.
So it's amazing how many sites he got. But then it's also important to define what information should be in the register, and how do you control the correctness of the information, and how do you keep it alive?
Right. Yeah. I think it's a good point. How do you keep this registry alive in time?
Yeah.
Thanks. Other questions? Do we have questions from online?
No, there's not.
Suzanne?
Not a question, just a piece of information. TCH on dam safety, and we were, as you mentioned, we're starting a new bulletin on risk assessment for dams, and we have the firm ambition to have tailings dam in the bulletin. So hopefully that will be useful.
Yeah. And I think that's improving within cooperation between the different committees.
Yes, we have somebody from your committee in our working group writing the bulletin. So hopefully, and he's very interested in risk, so I think there will be good cooperation.
I think that's our intention from our committee, to appoint one person who's responsible to overlook what another committee is doing. So we have allocated one person to each of the committees that are relevant for tailings.
Great idea.
Yeah.
Okay, then if we don't have other questions, we are perfectly on time and we can have our coffee break. And then we can reconvene in 30 minutes here, and we are gonna have this kind of 1 hour discussion about future of tailings dams. So now we can have our half an hour break. Thank you very much. Thank you very much for coming back on time. We can start with our future of tailings dam discussion. Well, the plan is that we don't have a plan for this. That's the main thing. We just have prepared some few slides, really few, with some points, just to trigger the
conversation.
Yeah.
Yes. We call it freestyle. So we just give you some bullet points and we want you to do the talking and not let us do the talking. So we want to kind of initiate discussions, and it could be anything, very stupid questions or discussions, arguments. That's the whole objective of actually having this workshop. So also for the participants online, so if you have any specific questions, comments, please post it in the chat. We have our phones here, so we can look at your comments on the chat, and we would have it included in our discussion. So please don't shy away. So you should kind of drop in, keep your comments coming.
Yep.
So we kind of have subdivided it into the different kind of sessions that we had during the last 2 days. So we start off with the geotechnical aspects, and then we kind of move into the run-out aspects of it, and then the geochemistry or the acid mine drainage, and eventually we look into risks and also about guidelines and standardization. So that's how we have chalked it out. But feel free to kind of go cross and cross-pollinate. That's what we basically want to initiate. So, we kind of look into, as I said in the first part, we try to look into some of the geotechnical aspects. So I'm just initiating it with one of the questions, that if you have a real tailings dam and you kind of, how do you think, how practical is it to actually define the critical state line for each of these layers? Like you have these slime layers, you have different layers which have been deposited over a period of time. And this question, which was also pulled up yesterday by one of our participants online, do you want it to be quasi-static, or do you want to reach a steady state? So somebody has comments in here. I know some obvious people who probably would like to open this discussion, but I would like to keep it open. And otherwise, I'm going to pick people.
Like at school.
Yes, like at school. So either you should wish that somebody else should kind of be the brave one, or you're going to make us pick. Okay. Somebody is very anxious. Yes, so Mike, do you want to start? Or maybe it could be more suited for Simon. So if you actually have a real tailings dam, so how much do you think we should focus on determining the, oh, sorry.
I guess since that was kind of the subject of my talk, it's fair that I answer it. I think in my view, it comes down to the degree of layering. I think there's certainly some great case studies where the layers are of a thickness that allows practical separation. I think Cadia was a good example of that, where they were able to pull it apart and look at each layer individually and then assign CSLs and NORSAM parameters in that case to each one. But there's certainly times where you're down at that micro lamination level where it's just impossible, and then in those cases I think you're stuck with having to look at it as a mass, and then really attack the uncertainty and sensitivity to the various potential impacts of fabric.
Like how much percentage of the industry do you actually think kind of relies on the critical state framework?
I'm going to let Mike answer that one.
Can you repeat that?
Like how much percentage of the industry do you think, like the practitioners, how many of them do you actually think rely on the critical state framework for tailings?
Okay, I've not done a survey. My own personal wish is those dams had fallen down 10 years earlier, because then I'd been very rich. From what I see for because we sort of support the CPT widget as an online freeware thing, but we get calls in to help use it occasionally. I would hazard a guess that most large companies are using this framework now. It's certainly much more widespread than it ever was. In terms of I'd also like to address some of the comments you got on the board here. It's not so much you have to define the critical state. What you need is the compressibility, the slope of the critical state line. You don't really care about the altitude. In fact, you don't care about the altitude where it is, because you're going to use a CPT, and CPT will give you the dilation angle, but that dilation angle depends on the lambda value you use in the inversion algorithm. So you've got to come up with the compressibility one way or the other. And when we came up with the Pluis method, which really addresses some of these questions, we said practically, with a multi-layered sounding with many layers and 20 meters, you can't do definition of the critical state line for every layer. So you've got to have to come off the CPT itself. So the CPT flags up your soil behavior type, and then you're going to have to associate critical state parameters to the soil behavior type. But that was my second point, is that when we put the Pluis method out, and that is used, I believe, by pretty well every company, that was the first toe in the water to make this possible. But the Pluis method is based on mid-80s data. And we know it doesn't work as well as it should do. And I think as a profession, we're going to have to improve the Pluis method, because that will address many of the points on your board. In terms of the quasi-steady state, if you're using Norsand, or for that matter, a bounding surface, you shouldn't be using the quasi-steady state as an input. Those models compute the quasi-steady state. The critical state has to be your reference condition. If I take my hat off as a civil engineer and I put my hat on as a physicist, it absolutely has to be the critical state, because that's where the physics is defined from. Now I think somebody else say, oh, I must answer your last question. How to model the initial stresses? You've got to measure them first. Right. So, we always shy away from the pressure meter, but you shouldn't. It's not as bad to use as you think. It is not necessarily as expensive as you think. And when you've done it, you'll learn to love it. You can actually, if you've got any modern constitutive model, bounding surface, CHASM doesn't compute it, but bounding surface or Norsand, we can actually compute K0. If you know what your calibration is, we can actually compute K0. But I still think it's affected by geological processes. So I've advocated and have done, it's not new for this workshop, I've advocated for like 30 years that K0 should be measured by pressure meters. And I put my money, or golf's money, where my mouth is. Yeah, self-bored. Yeah, you must use. Yeah, you have to use self-bored pressure meter.
Can I add one comment?
Yep.
I just want to add one comment to the last bullet, which is I also think there's an opportunity with respect to instrumentation to start installing load cells, multi-axis load cells in the ground as part of, becoming more routine in terms of, we install VWPs at every project site. It's not a tremendous obstacle to incorporate things like multi-axis load cells, so stress measurement as part of monitoring that would allow us to track stresses throughout the life of the facility as well.
Suzanne?
Yeah, sure. Since you're talking about K0, the first question I have when I see that, are you talking about K0 in the residues? And I think that's what we're talking here, huh? But there's also the K0 on the slope, and that's an entirely different value of K0. So, but in the residues, I agree that self-boring pressure meter is an excellent tool, but few people use it. I have a case right now that they're using Menard pressure meter, and that does not give you K0. And we did a fairly extensive research on K0 here at NGI many years ago, and in the field, what we found that was working best in ordinary clays was hydraulic fracturing. The cells were not as good as what we expected it would be. We've tried also measuring K0 in an odometer cell, and that has worked well, but there are very few K0 instrumented odometer cells in the world. So it is a problem, but the correlations that exist are fairly good based on other people's. But again, it depends on the state of the tailings. If the tailings are just new and very, very liquid, and then you can't measure K0, even with the self-boring pressure meter.
Continuing, there is a comment online. But even with a self-bore pressure meter, interpretation of the horizontal stress is not straightforward. Significant uncertainties remain. There is somebody there too who would like to. Okay, maybe.
Hi, so I'm from Cambridge in situ, so we do direct strain pressure meters, including the self-boring pressure meter, or the Cambridge self-boring pressure meter. We've used it recently on the tailings site, and we had really good results. And because we knew we were targeting horizontal stress as one of our key areas of interest, we actually designed the test procedure to focus on that, so looking at the traditional lift-off point, where you need a decent test and a really good, quiet self-boring in, but also looking at other processes, so the interpretation, looking at simple stuff like Marsland and Randolph. Again, it is an observational method. Looking at BPC, so looking at data post-plastic range, reloading it back up. So lots and lots of observational methods. And then you can start looking at the more interpretive methods of curve fitting. And we got quite good, or from the Cambridge side of things, we got quite good agreement. I know Mike did his own modelling as well, and we were in a similar sort of ballpark. Like, we weren't using the same techniques to analyse, but we reached similar conclusions. Yeah, but I do lots on pressure meters. Maybe we could have a chat later.
I'll also add another comment there, because somebody said that you mentioned about multi-axial load cells. Are there any studies comparing the horizontal stresses from load cells and pressure meters? So maybe you can do them together.
Yeah, I've not seen any where we've got both load cells and pressure meters. What I want to do is take objection to the idea that the pressure meter data is uncertain in its interpretation. I think if you're just relying on liftoff pressure, then yes, that has some uncertainty around the disturbance, which is unmeasured. But that's not the method we use to pull off data from pressure meter. You have to understand that the horizontal stress is carried throughout the expansion curve. Essentially, the horizontal stress scales the entire expansion curve. So the trick to getting reliable parameters out of the pressure meter test is you treat it formally as a boundary value test, and you then cast a model on it. You model the entire expansion curve, and you should model the entire unload contraction curve. And if you do that, you'll get quite nice repeatable results that are, I would say, very far from uncertain. It's also very easy to do in a spreadsheet. You can use John Carter's cavity expansion theory, just use his cylindrical solution, and it's three or four columns on a spreadsheet. It's not difficult to do. So people who say the pressure meter is uncertain, from my perspective, is they're just lazy in using the data.
So again, people want to hear about the local minimum of tailings, so what we discussed yesterday with Ramon, and I think we didn't really reach any conclusions, but the audience online probably want us to touch base again with this local minima that we observe.
Jorge, I think you need to reply.
Well, so finally, yesterday we agreed that we should use the quasi-state state of the minimal strength. That's difficult to obtain. And but today I am pessimist, and I have a problem with the CPT and with all things that we are doing here. First, in the case of tailings, we have a strong stratification. So the interpretation of CPT becomes a little bit complex. Second, in many cases, you have unsaturated part of the material. And people usually put everything together. It doesn't matter whether you are above or below the water table. And also, if you run the CPT test according to the standard with the certain speed, depending on the permeability of the material, you have drain response of the tailings, or partially drained, or undrained. And we have everything in the same bag, so we are not separating this. So what people usually do is engineering judgment. That's it. That is my impression. And people are very smart, very clever, have experience, and take the right number in general. But as everybody said, further research is needed. So that is my opinion with respect to the evaluation or characterization of tailings. Still, we have a lot of things to do. We know the problems, but all of them are very difficult to face. But the experience of the people so far, I think it can be used properly.
That could be taken in continuation with Michiel. Would like to answer the third one, like when you talk about this random fields. So when you probably want to kind of put it into perspective with respect to tailings, what do you think could be the most contributing randomness? Do we talk about state parameters, or also about the constitutive, like if you have different layers who basically behave quite different constitutively? So would you like to address that? So how could we handle something of that kind?
Okay, well, is this working? Yeah.
I think so.
I mean, if you've got very different layers, then you analyze each layer with a separate random field. And for each layer, well, at one extreme, at one end of the spectrum, what you could do is you could generate for each realization a separate random field for every single material parameter, and then cross-correlate between the parameters to account for parameter interdependency. But I wouldn't do that. I think the best thing is, basically, yes, to generate either a random field of state parameter or a random field of void ratio, for example. And for example, in the case of state parameter, what you would do is you would backfigure the other material parameters by having them as functions of state parameter. So once you've generated your state parameter random field, you automatically have all the other parameter values as well, and they are automatically correlated to the right degree. But certainly you would, if you have just very distinct layers, you would need to analyze each layer as a separate random field.
Another question, how small you would go with the layer?
Ooh. I don't know. I mean, certain. Yeah. I mean, I guess. I really don't know. I mean, normally we have normally with what we look at, we have very distinct sand layers or clay layers, so I don't know what it's like in a tailings dam, but you know, if we have a 1 meter clay layer, then we have a 1 meter layer. If we ever, I mean, eventually, obviously, if your layer gets very, very thin, then it becomes, from a numerical point of view, computationally impossible to analyze that.
Can CPT tell us a bit more about how we are going to schematize and discretize the
Well, there are ways that you can basically look at cone profiles and decide upon what the optimal number of different material zones is, and where the boundaries occur, and what the uncertainty associated with it is. So there are ways of automatically deciding on the layering in the vertical direction.
Yeah, I was just going to comment, if you're coming off the CPT, you've got to remember the physical limitations of the CPT. The friction sleeve is this long. You're not going to resolve lambda to a greater precision than that. The tip responds to about a meter of soil. You think a CPT is a small thing, but no, the tip actually loads quite a large volume of soil. So you're not going to look to great detail really with the tip. The pore pressure transducer is different. That certainly sees stuff at the centimeter scale, but you don't have the other information to go with that. So that, you know, you're coming off the CPT, that is your physical limitation. So there's no point asking about numerical modeling to a finer detail, because your input data doesn't have that information. What I think as a consulting engineer is stochastic studies are not viable in a consulting environment. What I think is what I've been advocating, and I've done this now for, I don't know, a decade, is the sort of things that Mike does should be done and then extract out of those. If we had to run with uniform properties, what would our choice of the value of the uniform property be? In Eurocode 7, that's what's known as the characteristic value, and I think we need many more studies as to what the characteristic value should be. The study I always refer to is the one published in Geotechnique in about '97, and I've never seen that study duplicated. And that's the study which is, you can look at it and make engineering judgment, and you say, okay, perhaps 80 percentile is the correct one to pick off. When I have applied it, I don't do, well, when I was at Gulf, we did formal processing to develop the 50 percentile. Now I just say to hell with it, I'll do it by eye. Ramon's engineering judgment, and that's what we applied on the Tara Island case history, and the judgment is described in that paper, and it worked really well, I thought.
Can we supplement it with some geophysical data when you talk about like layering, and we're just talking about CPT use, but is there any other technology or any other methodology that you think can help us better determine the layering or the profiling in a tailings dam? Or we just cannot think out of the box and we just have to rely on the CPT use and then keep bickering about it? Yeah.
Well, I guess we are looking at ways of basically cross-correlating shallow geophysical data with the CPTs in order to try and predict what the CPTs will be at other locations. So we are looking at that, and I think a number of people are looking at that. For example, I mean, if you need for wind farms, for example, that people are looking at ways of trying to cross-correlate between geophysical data and CPT data.
Farrokh?
I just have maybe a more fundamental question than this thing, because maybe these questions give the impression that if we knew all the layering and then we just do the CPT and come, then we could make a definite analysis and say this dam is safe, this dam is not safe, and so on. It just reminds me of this meeting we had a few months ago with our, when we were trying to sell NGI's expertise in tailings dams to a new company. And we started showing the numerical modeling, the back calculations we had done for these dams that had failed. And the client, which was obviously very experienced and clever, said, well, that doesn't impress me. Anybody comes to a dam that's failed, they're going to predict that it's failed, and they're going to predict the time of failure. Tell us about all the dams that you saved by doing your numerical analysis, that you prevented the failure. So on the spot, I had to save 3 tailings dams for him, but that's another story. But the thing is that second, I mean, we're talking about CPT, and it's like if we have this CPT, then we know everything. But that transformation, I mean, your CPT is kind of still you have to translate it to some other thing, to use it in your constitutive model and so on. And that transformation uncertainty gets you all the time. And this is not just tailings dams. I mean, we now are involved in many offshore wind farm projects where all the design is based on CPT. And this uncertainty we're finding out that it's becoming more and more critical. So all these correlations, okay, they look nice for the papers that are published, but in reality, there is uncertainty, and there are methods for dealing with it. But at the end of the day, I mean, the best you could do is to translate these things into some probabilistic, reliability-based statements. So you cannot come say, okay, this dam is safe because my numerical model says it's stable, and then this one is definitely going to fail. So I think we should maybe move away from this deterministic, definite, you know, that we know the lambda, so we can model every single layer and we can make a numerical model. And these numerical models, they're just idealizations at the end of the day anyway. So you really have to take a step back and say, okay, what do we learn from all these calculations, layering, and so on, and how can we reduce the risk at the end of the day?
I see a comment here. I'm not going to read it because I don't want to increase Farrokh's ego. Because there is someone that disagree. He says like great contribution from Farrokh.
Yes, so if I could add, like this person is, yes, oh, sorry. Go. Yes, three, yeah, go ahead.
Okay, I'd like to make some contribution with the CPT. I'd like to know if some guys have some experience with NMR technology that it's widely used in petroleum engineering, and now it's used in the environmental and hydrogeological study also. And with NMR, you can you don't have a 2 centimeters, but maybe a 20 centimeters layer, and you can measure the pore distribution, and you can measure the water distribution also in the soil. And I know that this technology is well known in the United States. I don't know if there are another guy with some experience with this technology. We are trying to bring this technology to Brazil to present to our clients, but as we are working with iron ore, there are some issues with the magnetic fields in iron ore, and we are trying to solve this with doing some lab tests there. But if you have another kind of waste, this technology probably will have some data, good data for these studies.
I can make a comment on that maybe, and then we can talk more later. But we do have an active project with NMR technology. Indeed, the challenge is the magnetic susceptibility that you have on many tailings. That, depending on the range of frequencies that you can have on the NMRs, it seems that you can, there is some promise and try to, interpret some results. But it's not only that. For saturated conditions, it's easier. But when you get into unsaturated conditions, even the signals that we are picking up with NMR, because it's just picking up an electromagnetic signal that is giving you a proxy to the number of protons that is having a medium. And then if you have air on that medium, that starts to be, a bit more complicated as well. And the other comment I wanted to make was on the shear wave velocity and or the geophysical and the CPT, and I want to put just that for discussion. Something we've seen sometimes on tailing deposits is that, for example, on seismic liquefaction, you can get very different responses when you measure the shear wave velocity because you have some sort of bonding or some sort of cementation, and you do the CPT and you get completely different response. The shear wave velocity, for instance, can be thought more as a small deformation. We're talking about small deformations over there. 10 to the minus 4%, something like that. CPT is a large deformation test. So I would be kind of curious to see what people think on correlating these very different scales in terms of properties. Thanks.
Yes?
Yeah. Now we're jumping a bit back and forth, but I just would like to comment on, or actually ask Farrokh something, because I'm not a tailing person at all, but when it comes to kind of going away from the deterministic approaches and rather over to the probabilistic approaches, we have the same discussions in the landslide field here in Norway. And I mean, when we then confront or have meetings with the regulators, of course they want a line, for example, in landslides. So my question then would be to you, how can we kind of overcome, I mean, how would we then get to guidelines that are still kind of handable for a regulator when we go away from the deterministic approach, which I agree that we should.
Yeah, so Regula, I'm not saying that we should completely get away from these guidelines, because I mean we're stuck with them for the foreseeable future. But as consultants or people who are giving advice to for some problem, at least we should be aware that these lines are kind of blurred boundaries. These are not very strict boundaries. And our capability of saying exactly where we are in this safety space has limitations. So, yeah.
Yeah, I fully agree. It's just for me, so far I have no good ideas how to kind of convey. It's kind of one thing to convey this uncertainty in a discussion and in a meeting, but then how to bring it into the guidelines. So it's, yeah, for me it's maybe more an open question that I think it will be interesting to dive into.
But that goes to what was discussed earlier, that how you translate these uncertainties into characteristic values and how those limits in the codes are defined. But there are, I mean, scientific ways of dealing with that. It doesn't have, of course, judgment can never be replaced, but there are ways of reconciling these two kind of apparently conflicting approaches, but they're not really conflicting. I mean, everybody wants to achieve the most safety possible, so that's the main goal.
We may have other questions that kind of take that will put this point on in terms of moving towards something that is more probabilistic, so that we can also move on with another set of questions here. We start with, we have seen from some presentations runout modeling, and sometimes in reliability or runout modeling is I would say from the beginning. What's the unstable mass that then we model as for the runout? And in this, the first point is, will 2D finite element model help identify critical cross-section and volume? This is maybe what do you think about, Scott? What do you think about that? Or Sun Chang also that was presenting something about runout modeling. How can we improve the reliability of the models in terms of prediction, not in terms of back calculation, where you know the initial volume, right? That the unstable volume.
Yeah, and I think what I presented yesterday, it was no surprise to anybody that the volume, the runout analysis results are very sensitive to the volume input, and that's true in the natural landslides realm as well. So that's been highlighted recently, in terms of debris flow prediction, for example, that the next frontier really is trying to constrain the initiation volumes much better than we can do right now, where we put so much effort into the runout analysis and not enough effort into constraining volumes. And I think, finite element modeling or even limit equilibrium modeling are tools that can be used to constrain failure surfaces and potential volumes.
For statistical correlation as well.
Yeah, and I think looking at case studies as well, yeah, so similar to the work that you've done, looking at correlations between release volume and storage volume, that's all important information. But I think it is a frontier, an open question, how do we constrain those volumes better?
But it links also with the GSTM standard that Yuuki was presenting today, because then the classification is made out of the consequences, right? In terms of how many people are exposed at risk. This is what the GSTM standard table refers to. So this is the other thing, the other point of how we do this runout, and then what are the inundation areas and how many people are potentially exposed. And this leads us to the second question, how to use the runout modeling results. Would you trust the prediction?
I remember yesterday from Scott's presentation that you had this pie chart where you kind of showed that the runout distances were for different tailing dams case studies. They were influenced by different parameters. So would you like to kind of rank, maybe if you were giving it a choice, what would be the top 3 that should be given the most attention to when you will actually kind of at least try to believe in the results for runout?
Yeah, that's a tough question. So I guess if we're talking about numerical modeling, then I would say in terms of inundation area, in general, it's not true for all of the case studies we looked at, but failure volume is a key parameter. So again, you know, trying to come up with methods to constrain that better is really important. That's also true for deposit depths. The failure volume is critical. Deposit depths are very sensitive to that. In terms of emergency preparedness and response planning, you know, obviously inundation area is important, but also arrival times and flow velocities. And in those cases, it's really the resistance parameters in the models that control those outputs. So I touched on it very briefly in my presentation yesterday, but trying to reconcile the differences between measured material properties. You know, we have rheological data for real tailings. Maybe we can look at rheology of mixtures of tailings and dam materials and entrained materials and so on, and trying to reconcile that with the input, the rheological inputs in the numerical models, I think is really important. And coming at it from a different direction, there are, you know, more advanced numerical models being developed that are more what Dick Iverson would refer to as more physically based, and where you could potentially actually measure material properties that have the same meaning within the numerical model. So I think pushing numerical modeling in that direction as well is useful. I've spoken a lot, but I think with the question, would you trust the prediction? It's also related to, you know, deterministic versus probabilistic. And I think it is tricky to communicate those results, and I know that there's reluctance to look at tailings dam breach analyses in a probabilistic way for that reason, that you know, the mine owner just wants a map that they can rely on for their emergency preparedness. One line and one estimate of arrival times. But there are analogs in other natural hazards. You know, for example, when you look at the hurricane, or I'm watching the news because Eastern Canada may be hit by a hurricane track very soon, and you know, when hurricane predictions are put out, they're shown as probabilistic maps, and people are used to seeing those hurricane tracks presented in a probabilistic way, and understanding that there's uncertainty with those predictions and that they need to be updated, you know, daily or even hourly. So I think that there's precedent for communicating that fairly clearly, and maybe we can learn from these other fields where that's done. Climate change predictions is another example.
Yeah, then there is another bullet point here. Will risk assessment help in setting the right priorities and making the right decisions? Magnus.
Maybe we would like to have some comments from the non-geotechnical engineers, have to have a different perspective. It looks like only the geotechnical things are important for a tailings dam, but it's unfortunately not the case. So we would like to have other opinions too. Yeah, go ahead.
Yes, while we're talking about these 5 bullet points, there is one important point I think we need to consider. It's when we do run-out modeling and inundation mapping, that they are done with different purposes. So we need to separate this. We do run-out modeling and inundation mapping to actually assess the dam consequence class. And that should, in my opinion, be done with conservative parameters, so that the dam is put in the right consequence class, because the opposite could mean that if you use too optimistic parameters, that the dam is actually put in a too low consequence class, and that impacts how much dam safety standard you put your dam safety program for the dam. The other thing you do run-out modeling and inundation mapping for is to assess the consequences of your failure modes, and to target to assess the risk better. And that, in my opinion, should be done with your kind of best estimate parameters, so you get the consequence correctly. And also those run-out and inundation maps for the separate failure mode should also be the one that the emergency plans and the municipality and so on gets, so they know what type of action to take depending on which failure mode that has occurred at a dam.
how you would quantify consequences.
How to quantify consequences. For example, according to GISTM, there is the table that, the guy from Hydro just showed us, but there are different quantification methods in different guidelines.
Maybe the last point that how do you like to, would you like it to be standardized? So, because as Regula also pointed out, that it's important that we communicate our kind of beliefs and findings to the stakeholder at the end of the day. So there should be a standardization of how we kind of define risk and how we communicate this risk. Everybody does it their own way, and then you're lost when you're probably on the same platform. So how do you think we should kind of initiate, or is there a need to kind of make risk to be standardized, the way we define risk for tailings? Maybe we do it for some other structures, but not for tailings. Some of the people who spoke about guidelines and standards, or somebody from the industry would like to take that. Nobody wants to talk about risk. It's a tricky thing.
Suzanne, we will.
Yeah, I'll bring that to you. Wait.
Oh.
You say everybody does it its own way, but not very many people do it for tailings dams. so that doesn't really work. But I have seen a number of analyses for tailings dam, and usually when they're done, they're compared to the probability of annual probability of failure and the consequences that come from a dam break analysis. With its limitation, we know that sometimes they may be conservative, but still the results are taken. They compare to risk diagrams that are similar to the one we use for water retaining dams. And for water retaining dams, we have guidelines in 10 different countries, which we have put them together, and then that provides a range of what we call acceptable and unacceptable risk. Now, nothing exists for tailings dams, you were right, but then not too many analyses are run either. But at this present time, it's maybe not wrong to compare it to water retaining dams. And if you think in terms of consequences, the life of the one person living downstream should be independent. The risk of losing your life independent, whether it's a tailings dams or a water retaining dam or a plane. It's early in the process to already set standards of acceptable, unacceptable risk for tailings dam, because there's very little experience with that. And even the statistics don't use. But how the acceptable, unacceptable risks were set for water retaining dam is based on what has happened before for the past 125 years and how many failures have occurred, and also comparing with what is the risk of living. I mean, when you're 2 to 10 years old, the probability of dying from any causes in the countries like Canada, United States, Australia, Norway, is about 10 to the minus 4 per year. And as you grow older, let's say you're 60 or 70, or let's say if you're 90 years old, the risk of dying in the next year is 10%. And that's a fact of life. So those things give you what we call a background estimation. And then, but again, it's never been discussed for tailings dams, so I think it's a bit early to try to standardize that.
But when we talk about risk, we don't really talk about environmental risks. So
yes,
how
environmental risk is also there. There's the risk to life. There's the risk of material damage. There's the risk of environmental damage. There's the risk of losing reputation. And the first two, material damage and environmental damage, usually translated in money. You will call low risk if it costs you less than, depending on the company, less than $500,000. But if it's more than $5 million, then it's called high risk or something. Yes, so there exists these type of guidelines too. But the most important to look at is the loss of life.
So how do the environmental engineers in the house kind of perceive risk? Like, is it on the same lines as how the geotechnical people do it? I'm pretty sure you do it in a different sense. And the thresholds are higher, lower? If you can throw some light, at least qualitatively, how do we assess geochemical risks or environmental risks? Just your opinion. I'm not asking for an expert advice, but maybe we can move on also to the next slide. Then you probably have, oh no, this is for the early warning system. No, this is more the other people.
Monitoring and.
But maybe then we should go forward and come back.
Yeah.
Yeah. So maybe this could be more. This is actually one of the questions that we got from a client very recently, that can we ever stop leachate treatment? They were so curious. They wanted us to come up with some data and correlate and tell them, okay, after 80 years, you could just stop doing it. Wait.
Thank you. Of course, that's the main objective. I mean, we actually a closure plan today, which would plan for long-term treatment plant, will not be accepted. I mean, treatment is good for some years, but it costs a lot, and we know that the companies are disappearing with time. So who is going to pay for that? That means the communities and the society, our taxes. So it's not acceptable to treat indefinitely. So that's why reclamation is important, and that has to be implemented right from the beginning of the operations to avoid treating the leachate for too long. So that's treatment is only temporary and should remain temporary.
But then that brings us to probably the next discussion when you talk about monitoring of these legacy dams. So the structural integrity monitoring and the environmental monitoring, how do you think this should keep happening, or there should be a point when you kind of call it that this is probably enough and then we just let the dams be there?
Yeah, that's another question actually. It's good practice to consider that there is no walk-away solution, that there will always be a need for some monitoring in the future, especially these days with climate change. We know that the situation is varying a lot, and even though we know a bit what to expect, we still not understand everything and predict everything yet. So even though there is no treatment, it doesn't mean that we just forget about these sites. So we just maintain them in good, just make sure that they continue to work as they are supposed to.
To keep the information over time, right? So, yeah, the information about where the tailings are and what is under the covers should also remain in the common knowledge. It's important.
Maybe we don't have a lot of time left.
No, we can.
We could go to this monitoring and early warning systems. So yesterday itself, I think it was rightly kind of brought up by Ramon that brittle failures is not something that can probably be predicted, but there are also other kind of failures. So does it kind of nullify that we shouldn't have or even think of developing any early warning systems just because brittle failures cannot be predicted? So we just say we don't want any systems to be engaged to predict or show any precursors. Yeah.
I just would like to come back to the question you asked before, because it's probably true. It's not. We don't talk about the same risk when it's about geochemical behavior of the tailing, because if you know enough about the material, you probably can predict a bit more. I mean, a bit more that it will, for example, oxidize. Right? Then it's just about quantitative knowledge in a way. Like if you know how much oxygen will come to the masses, you can predict how much will oxidize. While in, for example, failure we talk about in the other fields, then it's more about probability. It's a different. I think we talk about different risks in a way.
Yeah, I think what Sparsha was mentioning is that maybe analyze from the point of the hazard, but then what are the elements at risk, like the environment? What's the risk of polluting the environment and the fauna, right? So maybe this is maybe what we were thinking, but in your case, you are thinking only at the phenomena itself of happening or not happening, not so much thinking about element exposed, right? Or things exposed, that elements that can be environment or can be people or this was the
environmental risk assessments are also starting to be more and more seen in the and we actually get inspiration from the what has been done in geotechnical risk for a bit longer actually, and especially outside the mining area for civil infrastructure. So we get inspiration from that and we try to apply. But yeah, the main difficulty is how do you quantify the risk. And Suzanne, maybe you can comment on that, because it's not in terms of costs, it's not in terms of loss of life, it's something else, it's loss of biodiversity, for instance. So it's difficult to quantify it, and that's very often what's the limitation to the application of this risk analysis to environmental engineering.
Then
well, the loss of nature and biodiversity, I think they can attach a cost to it. But the level of pollution, the pH being higher than 12, or some silicate going in nature, I think that has to be quantified by the quantity or the damage it will do. So those are not very easy to quantify, but they can be quantified in terms of what you don't want to happen. Say, so if you don't want a pH greater than 9, which is in one of my cases in Scotland, then that's the limit. And so we're looking at the risk of having a pH greater than 9 from the contents and the chemicals and such. But I don't have a good answer for the amount of pollution, because, as you said, it's only starting now doing these type of risk assessment.
And then, Jerome?
I am pretty surprised about your answer about the question of stopping the treatment. Do you have actual example of closed TSF producing leachate that where they were successful to stop the treatment?
Yes, several ones. For example, LTA in Quebec. For example, well, yeah, I mean, several of the closed mine sites which have been where they've been using oxygen barriers have been working well. And LTA that I was mentioning is actually was a site which was producing a lot of acid because it had been abandoned. Then it was reclaimed. And even though it was complex, as Gabrielle has mentioned this morning, it works. It works very well.
They close the TSF, and a couple of years after, they add an oxygen barrier.
Actually, what happened is that actually they didn't do anything. It started to produce acid mine drainage. Then the government, which had the responsibility after the company went bankrupt, decided to do the reclamation. They did, and it was closed into the reclamation was done in 2004, I think, and for the last almost 20 years they have been controlling the water quality, and it's respecting the standards.
This leads us to this last slide about monitoring and warning, and just repeating what Sparsha was mentioning. Can a warning system, we mean not only monitoring. Monitoring is not really warning system. Monitoring plus modeling can help to avoid failure. And if we have a brittle failure, can at least help to reduce losses. My question maybe goes to Kai from Titania. And I mean, did you have early warning in place if things were going wrong? At least to reduce the losses, right? Human mostly.
So when in this project that we presented, we really had a focus on
on the emergency plans for reclassification of the dam. So then we involved the local municipality, the police, and all the emergency rescuers who would be involved in case of emergency. And that was a huge job because the local community needed also to revert their plan, and we also between a border between two regions, so we needed to also include both Sokndal, the local, and Flekkefjord, who was the neighbor. And then how were the plan working together if there was going to be evacuation of the area. We also saw that there was raised questions to the company as an owner. That the owner had the responsibility for evacuation, or who has the responsibility if in case of an emergency. We were able to land that also because it is the owner of the dam is responsible for the technical that we need to advise, and in case that we recommend evacuation, the police will be the one that take the final decisions. But we did establish a lot of different instruments to keep a tight monitoring of the dam, and also the evacuation system alarms was also installed in Onasira during this project.
What parameters were you monitoring? This can lead us to the other two questions.
So we had deformation, the water levels, vibration, and in deformations we also had the radar system as well. So we had two systems on deformation. We had volume on the seepage and turbidity, or the sediment in the water that seeped out of the dam. This was the different monitoring that we had on the TSF.
Yeah, thanks. But this question is open to everybody, both
Emanuele?
geotechnical engineers and also environmental engineer. What parameters would you monitor for your different issues that you may deal with? Yeah, Emanuele, please.
Thank you. I wanted to answer to the first or both the first and the second questions by presenting an example from landslides, which is my background. We are now, for example, experimenting Doppler radar, which is a radar that is used to detect rockfalls. So rockfalls are obviously very brittle, and you don't measure the deformation. You see them as they fall, but this gives you some tens of seconds of lead time that can be enough to close a street, for example. And if people living in the area at risk, they know what to do. Maybe they just hear the siren, then they know that they have to do something. And in tailings, then you are able to reach the people that are at risk. So this part concerning the education of the population, the people at risk, the workers, is somewhat doable. And so even if you have very sudden and abrupt collapses, but you have maybe I'm not saying that we are able to do that right now, but if there is the possibility to see some precursors that last for even 1 minute or something like that, that still could be, I think, could be something that could be useful. Of course, you don't prevent environmental damage and material damage just for human lives, but 1 minute, tenths of a second, they can be enough. So, of course, not using satellite, as I shown earlier today, maybe using GBINSAR, or maybe not. Maybe we need something else entirely. But even though the collapse is sudden, still we should not dismiss this very short lead time as something that is useless.
Thanks. Any other comments? Yeah, Ramon, please.
Yeah, I think by definition, a brittle failure, it occurs suddenly. So it's just the definition. Otherwise, it's not a brittle failure. For example, you have a tailing that has some problem in the stability, and there is one small earthquake or medium earthquake. That failure will cut the pace immediately during the earthquake. So there's nothing to do. You will know that the failure will occur in the next 2 minutes. So nothing to do. So for that type of failure, my impression is there is no way. So only the people that are in charge of the design must prove that there is no possibility of a brittle failure. Then, because of other problem, you should have always a warning system for any other type of failure.
Okay, this is my question for you. Do you think that if something happens, a brittle failure, instantaneously, you can push a button and give an alarm, and maybe people living downstream may be saved? You think that, or you don't think that?
No, I don't think so. Because that creates the idea that you are somehow controlling that.
Okay.
So I prefer to feel like I don't have anything to do, so I have to do the right design and check everything in order to don't have a brittle failure.
Interesting point.
That's my point. So a brittle failure must be avoided by any means.
Okay.
But always there are some problems. So in that case, you always need a warning system.
Just to reinforce the point Ramon is making here, if you look to structural engineering, and we do reinforced concrete, we always put the reinforcement in there to ensure that any failure is ductile. It's in our structural codes. And into those columns.
Yeah. No, but maybe if others have other kind of other parameters you want to.
Because anything else that you want to bring to the table? Yes. Good. Yeah.
Thank you. I just want to get back a little bit to the monitoring, and one point, since we are talking also about the remote sensing and the early warning system, another point could be indirectly related to that is the forensic ability to utilize remote sensing. And actually we have applied that for a water dam failure in Australia, where we could use the NSAR monitoring to justify or pinpoint the causes. So maybe Emanuele could comment on that ability. The point mentioning aside than the early warning system is the ability to utilize NSAR for forensic application in dams failure.
Well, that actually is something that in Florence we try to develop a faculty, or not how to say, a study course on forensic geology, just because of this. And yeah, I think that it's actually what we see in many papers today is just what you are saying now. Actually, probably we already have more forensic cases, as you said, than actual forecasting for several reasons. One reason is that, at least from my experience, it's very difficult to have the correct, a good availability of data that allow you to have something that is not forensic. So you always have to end up making forensic evaluation at the end. And I think it's very often a problem of data availability. That is something that we have seen in these days also in other fields.
Yeah, okay. I think we can either go to the very last thing, right?
Yes, so we just thought we have something like it's a last moment addition to just demonstrate what the mining industry is up to and what the future of tailings could look like. So we would have to have on stage Joao from Vale, and they would like to he would like to demonstrate the new experimental setup that they have built that could, yes, we could use the microphone, the handheld one. Yes. Could we move to, could we move to the 11B? Yeah.
Hello, everyone. It's a pleasure to be here. I'd like to say thank you for NGI and for Sparta for inviting me to share with you some our initiative inside Vale.
The top one, this one, takes you forward.
Yeah. Okay.
That's the pointer. Yeah.
I work in a Vale Geotechnical laboratory. It is located in Mineral Development Center of Vale in Santa Luzia, Minas Gerais. The Vale Geotechnical Laboratory was founded in 2018, and we support our operations and projects in Brazil and worldwide. We seek to improve solutions to have safer geotechnical structure in the mining industry, exchange experience with research centers around the world, and contribution to advancement of knowledge in geotechnical area is we intend to do. We have 3 labs, a soil mechanics lab inside Vale, a rock mechanics, and a field test. And here is a picture of our team. We are all around 30 people, engineers, geologists, and technicians. The initiative that I was, sorry for this. The initiative that I will talk a little bit about is the calibration chamber. That's something that correlates with Mike speak yesterday. So we developed a calibration chamber for try to get more confident information about the CP2 tests, which is the calibration chamber. Looks like a big triaxial. We have ability to put a radial pressure up to 4 megapascals, axial pressure up to 2.2 megapascals, and we also have the ability to impose a back pressure up to 2 megapascals. The difference of this equipment for you buy from GDS is just you have a little bit bigger, is a 1.5 meter of diameters by 1.2 meters of height. And the second difference is that we have some space. Some space in the top to push the cone. It's a standard cone. We are working with the standard. It's a gel mill cone. It's a digital cone, but It's a regular one, and we also have ability to have also 3 other signs to try to answer the question of Mike made yesterday about the scaling of the cone. So we have a 5 centimeter, 10 centimeter, and 15 centimeter cones in this chamber. We can run tests from with a standard velocity and slowly, very slowly velocity, and up to 5 times the standard velocity. Here, something more about our equipment is how I told you is a kind of triaxial. We have a membrane here. Here is the chamber. In our chamber, we have the bottom cap and top cap, a space for power stones. In the top cap, we have space for three cones. Try to help to get more information from this big sample. Here we have inside this chamber the splitted mode, is a contractive, and we also have radial displacement, 9 sensor of radial displacement. Mike told us that this test spend around 2 tons of material. It's not true. We spend around 4 tons. And we also have inside this equipment a kind of bender, looks like more a cross-hole test. We have 4 geophones in each side of the equipment with the trigger for make something like a cross-hole tomography to help us to understand how the material is. We have some pictures here about the equipment. Here's the frame. It's a big frame for 400 tons, because how we have 1.5 meters is we need force for that, and to allow to take to put material in the upper part is we can open the upper part. Here are some pictures about the equipment. We are almost finished the construction. The project was, we spent almost 1 year in projects. We constructed, it spent more time than we imagined and spend more money, but it's always happened. Here is one view of the top of the bottom cap with some power stones. These power stones in the future, how we have tailings done, but now we start to have dry stacking tailings. So we think in the future change this power stone for high R pressure enter, but it's not for now. It's just an idea, but we have space for that. Around here is the splitted mode. Here is some figure of the equipment. Here is the membrane, like the triaxial a little bit. And here is the guy put material for tuning the equipment. We are tuning the equipment now. We believe that we will finish the tuning until December and start with the tests. Here is one view of the equipment from bottom to up. And this connections is for the instrumentation and displacement, and also for contract the splitted mode. So from now, we have some QR code that with a small video about our other initiatives in our geotechnical laboratory. And we are working with, we have a problem. Our schedule is tuning the equipment until end of this year. In the next year, we will start playing with sands because it's easy. And also because we intend to get more confidence in the equipment and get correlations with the available information about the calibration chamber, other calibration chambers. So we intend to spend until July with sands, which sample in sands spend around 2 weeks. After that, we intend to start with tailings. In this case, we will spend something, we believe that we spend something like 3 or 4 weeks for each specimen. And after that, we'll have the numbers, but we need to knowledge. So we have a partnership with University of Toronto, Professor Gaza, to help us to modeling the results and bring more information from the data. The guys that are factoring the equipment is Mascolo guys. They help us in the project. And here is one view of our equipment. Just for scaling from the bottom to the top when it's open, we have around 7 meters. And that's it. Thank you very much for your attention.
Yeah, thank you very much for this short description of your going on activity. I think we can move on towards the closure with Dominic Lang, and then after Dominic closure, we may give you some few practical information about what's going on.
I think Dominic does it himself.
Okay. Great.
So we're going to head for the dinner after that. So I think it's okay if you're a bit delayed. So yeah, sorry for that.
Thank you. Yes, quite some 2 intensive days. I wanted to use the opportunity to wrap up a bit, both technically from my point of view, and also give you some practical information. Of course, also thank a couple of persons. So again, this event has been sponsored by a number of partners, so thank you again for that. We hope that we kind of fulfilled your expectations with that. It's becoming more and more critical to have some industry sponsors to conduct events like this. So thank you, very much appreciated. So just some closing remarks. As I probably told, I'm not working directly with tailings dams. I wouldn't call myself a geotechnical engineer, but I'm an engineer, so I have some understanding of the thing. So what we've learned during these past 2 days. The first thing is conducting additional laboratory tests is essential to gain a deeper understanding of intermediate soils. Acknowledging and accounting for uncertainty is crucial, and adopting a probabilistic framework is a prudent approach. I know that many have problems with probabilistic approaches. We see that in all types of disciplines, and this is really becoming crucial, and I think here there's a lot of potential to also further educate ourselves. Further, implementing both structural and environmental monitoring over the long term is necessary to create sustainability. We've seen this also in many presentations today, also with what Thomas presented, like this multidisciplinary approach, like where expertise, hydrochemical, hydrogeological, geochemical, geotechnical engineering is working together. I mean, this is a trend that's going on in all disciplines, and it's becoming more and more crucial to really make a difference. And then this making decision based on consequences is increasingly important. So basically using a risk-based approach, not only in geotechnical engineering in general, we see that also probably the approach is maybe coming even from engineering seismology and earthquake engineering. And also bridging the gap between research findings and practical application in the mining industry is vital. So this also, of course, is necessary that mine operators and mining companies are probably investing a little bit of more money now in the future to really like fund universities and PhD students, master students to conduct valuable research. We've also kind of gathered a few ideas how we could increase collaboration, and we should not use this event as a basically marketing opportunity. But from NGI's perspective, what we basically, from the offer side, is that we could, of course, conduct more regional workshops or more customized training courses for some companies, not only with NGI, but also in close collaboration with other partners, universities, research institutes, and mine operators. We would also offer you to think about supervising that NGI or also our partner network would be available for supervising master and PhD thesis. I know that there are many young mining engineers that would further educate themselves, and sometimes it's really not so easy to really make the first step into this direction. Another thing when it comes to the scaling up of research and maybe identifying the problems and working on problems that are not so covered by daily operations is the idea of initiating a joint industry project, which is, I think, a concept that's coming from the offshore industry, where a lot of competitive companies have a common problem, and they all put together a little bit of money in a pool, and then a consortium of research partners is basically working on a problem and sharing the research findings with the whole consortium. And another thing, this is of course more relevant for the European partners that are in the house. Horizon Europe, I think it's probably the world's largest research and development program. They are now gearing up towards the mining operations, mine cycle operations and things like that. So we've seen, yesterday I presented that we've recently won 2 large Horizon projects. This is of course depending upon opportunities, what the further work programs that are coming out in Horizon Europe will bring. But I mean, here there is definitely a potential to maybe some of us working together in future on a few of these proposals. Or I can also just offer you to directly take contact with us. There were a lot of people from NGI present yesterday and today and also tomorrow. So please come up and with your suggestions. First of all, I wanted to also thank all the presenters. That was really a very fantastic group. And when I was mingling during the past 2 days, everybody, first of all, said, what a fantastic program. And the program is not that we put this together. The program is basically these presenters that really presented a very broad variety of the state of the art of this important topic. So thank you to you all for taking the time, putting your time into working on your presentations and also coming to Oslo and presenting this to us. Thank you so much. Yeah, that's it. But I also want to thank you all that have not presented for just coming and joining us here. It would be sad if we would here have a full hybrid mode or an online workshop over 2 days. We all know from the past years that during COVID, I think all of us catched ourselves subscribing to some of these online courses, and then after a couple of minutes, probably phasing out, sleeping, or doing something else which was more important. So being present, being here in the room is very valuable. But I also want to thank the participants that joined us online. I think it's almost 40, which we didn't expect. It was always also difficult to judge, shall we use money to do the streaming in a professional way. I hope that all these online participants really also got a lot of back from this event. So thank you for that. But of course, also I want to, foremost, today I wrote in our intranet, 2 stars are born, and Sparsha and Luca, I think they did an amazing job. You have no idea how much, bloodshed and tears that they put into this event. There were, I wouldn't say sleepless nights. I wouldn't say sleepless nights because they don't deal with the finances. That's my job, but they really put a lot of effort in it, and especially during the past weeks, we almost, daily, several times a day, we were in contact, and it was very, very, satisfying me to see from my point of view that I'm not needed. So thank you for that. But also, of course, Kirsten, that very good took care of us, my assistant, thank you. And the ladies from the communication department of NGI did a fantastic job with like the LinkedIn posts and things. And also a great thanks, of course, to Håkon, who is leading the section where tailings dams and dam safety is going in. And of course, Suzanne, I didn't forget you, but Suzanne, we all know that these guys only come to see you, so thank you for that. So just some practical information. Dinner tonight at 6 o'clock, so we can maybe mingle a little bit around here. It's also beautiful weather. You can just go outside. It's probably a walk of maximum 5 minutes. You can also go around the opera. It's a beautiful walk along the water. So we meet there at 6 o'clock, and it's a classical pizzeria, quite nice food. And tomorrow, quite important for those of you who decided to stay and come to our temporary offices. As you know, I think we've told we are currently constructing a new campus building that will be finished hopefully in 2026. NGI main office in Nydalen, so you basically take subway, T-bane, number 4 and 5, get out at stop Nydalen, and then it's approximately a 5-minute walk. If all of you can use Google Maps, so I'm pretty sure you will find it. And remember, the world is run by those willing to sit until the end of meeting. So tomorrow will be important. And for that, I want to thank you all again for being here. I want to thank all of the participants being online. And yeah, hope to see you again in Oslo. Thank you.
Yeah, very last thing. So we can say goodbye. So see you tomorrow to the people attending online, because we managed to send them a link so they can follow our, at least the first